Welcome to Sleepy Science Student, where we explore the cosmos one gentle whisper at a time. Tonight, we're going on a slow, peaceful journey into one of cosmology's most curious mysteries, the possibility that everything in our universe might be spinning around a single, hidden point. It's a story written in ancient light, in the synchronized dance of distant galaxies, and in patterns so subtle they took decades to even notice. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something fascinating about the universe's deepest symmetries in the process. Not the worst way to spend a sleepless night. Before we drift into this cosmic mystery together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this quiet little channel grow and means more curious minds can find their way here, gently, one video at a time. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Melbourne at 2 a.m. or listening from a window seat in Oslo at sunset while watching the last light fade? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all of us wondering about the same distant stars. Now settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert or worry about understanding every detail. Just let the words wash over you like starlight falling through an open window. Let your shoulders relax. Let your breathing slow. And as we begin this gentle voyage into cosmic alignment and universal symmetry, remember this video is for educational and relaxation purposes only. It's not intended as astrophysical advice, though it might make you see the night sky a little differently. Ready? Let's begin. Let's start with something simple, something you might think is just noise. In 1992, a satellite called COBE, the Cosmic Background Explorer, was listening to the universe. Not with ears, of course, but with sensitive instruments designed to detect the oldest light in existence. This light, called the Cosmic Microwave Background, or CMB, is a faint glow that fills all of space. It's the afterglow of the Big Bang, stretched and cooled over 13.8 billion years, until it's now just a whisper of microwaves, barely warmer than absolute zero. Scientists expected this ancient light to be almost perfectly uniform. Almost, but not quite. They knew there would be tiny temperature variations, little hot spots and cold spots spread randomly across the sky, like freckles on skin. These variations are important. They're the seeds from which galaxies grew. Where the CMB was slightly warmer, matter was slightly denser, and gravity could pull things together more easily. But when the COBE team looked at their data, they noticed something peculiar, something that shouldn't have been there. The temperature variations weren't quite as random as they should have been. There was a pattern, a very subtle pattern, like a watermark hidden in the fabric of space itself. Imagine you're looking at a painting. From far away, it looks like random brushstrokes, chaotic and unplanned. But as you step closer, you start to see that the brushstrokes aren't quite random. They're all tilted in the same direction, ever so slightly. Not enough to be obvious, but enough that once you notice it, you can't unsee it. That's what the COBE team found in the cosmic background radiation. This pattern became known as the axis of evil. Don't worry, it's not actually evil. The name is a bit of scientific humor, a playful reference to a phrase from politics that happened to be in the news when the pattern was discovered. But the name stuck, and it captures the unsettling nature of what was found. An axis, a direction, a cosmic alignment that shouldn't exist. You see, according to the cosmological principle, one of the foundations of modern cosmology, the universe should look the same in all directions. If you could float in space and spin around, the universe should appear statistically identical no matter which way you face. There should be no preferred direction, no cosmic up or down, no universal North Pole. The universe should be isotropic, meaning it has the same properties everywhere and in every direction. But this axis suggested otherwise. It suggested that maybe, just maybe, the universe does have a preferred direction, a hidden alignment, an orientation. At first, scientists were skeptical. Data from space missions is tricky. There are so many things that can introduce artifacts, instrumental errors, interference from our own galaxy, subtle calibration issues. The COBE satellite, while revolutionary, wasn't perfect. Maybe this axis was just a glitch, a shadow cast by imperfect instruments. So they waited. They built better satellites. They collected more data. They hoped the axis would go away. It didn't. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. This satellite was far more sensitive than COBE. It could measure the CMB with exquisite precision, mapping temperature variations down to millionths of a degree. WMAP spent 9 years staring at the ancient light, building the most detailed picture of the early universe ever created. And when scientists analyzed WMAP's data, they found the axis again. Still there, still subtle, still unsettling. The pattern showed up in the lowest multipole moments, the largest scale patterns in the CMB. These are the features that stretch across the entire sky, the broadest brushstrokes in the cosmic painting. Specifically, they noticed that the quadrupole and octupole moments, technical terms for certain mathematical patterns in the CMB, were aligned with each other in a way that seemed statistically unlikely. Imagine rolling 2 dice and getting the same number, but not just once. Getting the same number over and over, in ways that probability says shouldn't happen very often. That's what the alignment looked like. Even stranger, this cosmic axis seemed to point in a particular direction. When scientists traced the alignment back, they found it roughly lined up with the ecliptic plane, the flat disk of our solar system. It also aligned, eerily, with the direction of Earth's equator projected onto the sky. This was deeply troubling. Why would the largest structures in the universe care about our tiny solar system? Why would patterns from the Big Bang, formed billions of years before Earth existed, align with the plane of our planet's orbit? It made no sense. It felt wrong. It felt like finding your home address written in the stars. The scientific community proposed explanations. Maybe it was foreground contamination, light from our own Milky Way galaxy getting mixed up with the CMB. Maybe it was a statistical fluke, a random coincidence that looked meaningful but wasn't. Maybe it was something else entirely, some subtle effect no one had thought of yet. But the axis remained. Quiet, persistent, patient. In 2009, the European Space Agency launched Planck, the most sophisticated CMB observatory ever built. Planck had even better resolution than WMAP, even more sensitive detectors, even more careful calibration. If the axis was an artifact, Planck would expose it. If it was real, Planck would confirm it beyond doubt. Years passed, data accumulated. Scientists processed millions of measurements, filtering out every possible source of contamination. They accounted for dust in our galaxy. They corrected for the motion of our solar system through space. They tested their instruments obsessively, looking for any flaw that might create a false pattern. And then Planck's results came in. The axis was still there, perhaps even slightly stronger than before. The alignment of the quadrupole and octupole moments persisted. The correlation with our solar system's orientation remained, strange and unexplained. Some researchers began to call it the CMB anomaly instead of the axis of evil, trying to strip away the dramatic language and focus on the science. But whatever you called it, the implication was the same. The universe might have a preferred direction, a cosmic alignment, an orientation woven into the fabric of space-time itself. Now let's pause for a moment. Take a breath. This is where science becomes both beautiful and uncomfortable, because what we're discussing isn't just an interesting curiosity. It's a potential crack in one of our most fundamental assumptions about reality. The idea that the universe is isotropic, the same in all directions, is built into Einstein's equations. It's the foundation of the Big Bang model. It's why we can use observations from our small corner of the universe to understand the whole cosmos. If the universe truly has a preferred direction, everything changes. Not in a dramatic, earth-shattering way, Science doesn't collapse, but it shifts. It adapts. It grows to accommodate new truth, the way a tree grows around an obstacle. And this is just the beginning of the story, because the CMB isn't the only place where hints of a cosmic axis have appeared. There are other clues scattered across different kinds of observations, different wavelengths of light, different distances in space. And as we'll explore gently through this long night together, these clues paint a picture that's both fascinating and deeply mysterious. The universe might be spinning, or at least everything in it might be organized around a hidden line, an invisible pole, a cosmic axis we never expected to find. But before we explore those other clues, let's take a moment to understand what we're actually looking at when we talk about the cosmic microwave background. Because this ancient light is one of the most remarkable things in all of science, and understanding it, even just a little, will help everything else make sense. The CMB is everywhere. Right now, as you lie there, you're bathed in it. Microwaves from the Big Bang are passing through your body, through your walls, through everything around you. They're invisible to your eyes, but if you could see in the microwave part of the spectrum, the whole sky would glow with a soft, uniform light. No stars, no galaxies, just a gentle, all-encompassing radiance. This light was created about 380,000 years after the Big Bang. Before that moment, the universe was too hot and dense for light to travel freely. Photons, particles of light, would be created, only to immediately bump into free electrons and scatter in different directions. The universe was opaque, like a thick fog, but as the universe expanded, it cooled. And at a certain temperature, about 3,000 degrees Kelvin, something remarkable happened. Electrons combined with protons to form neutral hydrogen atoms. This process is called recombination, though technically it should be called combination since it was the first time, not a recombination. But the name stuck, and scientists are stubborn about changing terminology. When recombination happened, light was suddenly free to travel. The fog cleared. Photons that had been trapped began streaming outward in all directions, carrying with them a snapshot of what the universe looked like at that moment. And that light has been traveling ever since, for 13.8 billion years, stretched by the expansion of space from visible light into microwaves. When we look at the CMB, we're not looking at stars or galaxies. We're looking back in time, seeing the universe as it was when it was just a baby, 380,000 years old. We're seeing the pattern of hot and cold regions that eventually became the large-scale structure of everything, the clusters and superclusters and voids that fill space today. It's a bit like looking at a photograph of a forest when it was just seeds scattered across the ground. The trees don't exist yet, but the pattern of seeds determines where they'll grow. The CMB is that pattern, the earliest pattern, the template from which everything else emerged, and embedded in that pattern, subtle and strange, is this axis, this alignment, this hint that the universe might not be quite as symmetrical as we thought. Now, you might be wondering, how do scientists actually measure something like this? How do you take the temperature of the entire sky? How do you find patterns in something as faint and uniform as the CMB? The answer involves mathematics, specifically a technique called spherical harmonic analysis. Don't worry, you don't need to understand the math, but the basic idea is simple enough. Imagine you're trying to describe the surface of a bumpy sphere, say a golf ball. You could describe it by saying, there's a dimple here, and another dimple there, and another over there, listing the location of every feature. But that would take forever, and it wouldn't give you any sense of the overall pattern. Instead, you could break the surface down into a series of patterns at different scales. Large, smooth variations across the whole sphere. Medium variations that repeat a few times around the circumference. Small variations that create fine details. By adding up all these patterns, these harmonics, you can reconstruct the original surface. That's what spherical harmonic analysis does. It breaks the CMB down into components at different angular scales. The quadrupole is a pattern that divides the sky into 4 regions, 2 hot and 2 cold. The octupole divides it into 8 regions. Higher multipoles create finer and finer details. Each of these patterns has an orientation. The quadrupole could be aligned with the north-south axis of the sky, or the east-west axis, or any direction in between. In a truly isotropic universe, these orientations should be random. The quadrupole might point one way, the octupole another way, with no relationship between them. But in our universe, they align. The quadrupole and octupole point in nearly the same direction. And that direction, bizarrely, correlates with the plane of our solar system and the orientation of Earth's equator. This is the axis of evil. This is the pattern that refuses to go away. And this is where our gentle journey into cosmic mysteries truly begins. Because if the universe has a preferred direction, we need to ask, why? What could cause such an alignment? Is it telling us something about the Big Bang? About the shape of space? About the nature of reality itself? Or is it, despite all the careful measurements, still just a coincidence, a statistical fluke that happens to look meaningful, but ultimately signifies nothing? These are the questions we'll explore as we drift through the night together, slowly, gently, with no rush to reach any conclusions. Because the universe is patient, and mysteries are often more beautiful than answers. Let your mind relax. Let these ideas float past you like clouds. You don't need to grasp them tightly. Just let them drift by, one after another, painting pictures in your thoughts as you settle deeper into comfort. We have a long way to go, and we're in no hurry to get there. Now, let's talk about rotation, about spin, about the way things in the universe seem to have a preference for turning. Everything in the universe spins. Planets spin on their axes. Moons orbit planets. Planets orbit stars. Stars orbit the centers of galaxies. Even galaxies themselves rotate, their spiral arms sweeping through space like water swirling down a drain. This isn't surprising. Spin is natural. It's what happens when something forms from a rotating cloud of material. As the cloud collapses under gravity, conservation of angular momentum, a fundamental law of physics, causes it to spin faster, like an ice skater pulling in their arms. The result is that almost every object in the cosmos has some rotational motion. But here's the interesting part. The direction of spin should be random. If you look at 1,000 galaxies, roughly half should be spinning clockwise and half counterclockwise from your perspective. There should be no preference, no bias, no overall pattern. Each galaxy's spin is determined by the local conditions where it formed, which should be independent of other galaxies far away. At least, that's the theory, and for the most part, it holds up. When astronomers look at nearby galaxies, they find the expected random distribution of spin directions. No pattern, no preferred orientation, just the statistical noise you'd expect from truly random processes. But when you look farther out, at very distant galaxies, billions of light years away, something curious begins to emerge. Something that echoes the CMB axis, whispered softly in the shapes and orientations of spiral galaxies across the cosmos. In 2011, a physicist named Michael Longo published a study that caught the attention of the astronomical community. Longo had been analyzing images from the Sloan Digital Sky Survey, or SDSS, one of the most ambitious mapping projects in astronomy. The SDSS used a dedicated telescope in New Mexico to photograph huge swaths of the sky, creating a detailed catalogue of millions of galaxies. Longo focused on spiral galaxies, the beautiful pinwheel-shaped systems like our own Milky Way. He carefully classified them based on the direction of their spiral arms, determining which way each galaxy was spinning. This is trickier than it sounds, because you have to account for the galaxy's orientation. A galaxy viewed edge-on looks different from one viewed face-on, and you have to work backward from the observed shape to figure out the true rotation direction. After analyzing tens of thousands of galaxies in the northern galactic hemisphere, the half of the sky above the plane of our Milky Way, Longo found something unexpected. There was a slight but statistically significant excess of galaxies with left-handed spins. Not a huge effect, not something that jumps out at you, but enough that it was unlikely to be pure chance. In the southern galactic hemisphere, he found the opposite, a slight excess of right-handed spins. It was as if the universe had a weak rotational preference aligned with the axis of our own galaxy. Other researchers were skeptical. Sample selection effects, they argued. Measurement errors. The human eye seeing patterns where none exist. Longo's work was intriguing, but it needed confirmation from independent studies. And confirmation came, though not always in the ways people expected. Over the next decade, several other studies found similar hints of large-scale alignment in galaxy spins. Some confirmed Longo's results. Others found different patterns, or no pattern at all. The picture became complex, murky, difficult to interpret. But then, in 2020, a study using a completely different approach reignited the controversy. Instead of using human classification of spiral arms, this new study used automated algorithms to measure the three-dimensional orientations of galaxies, accounting for their viewing angles and using more sophisticated statistical methods. The results showed a weak but consistent alignment of galaxy spin axes across huge volumes of space, structures stretching across 1 billion light-years or more. The alignment wasn't perfect. It wasn't as if all galaxies were spinning in exactly the same direction, but there was a correlation, a tendency, a bias in the data that shouldn't exist in a perfectly isotropic universe. Imagine a field of flowers, each one oriented randomly. From above, you'd expect to see them facing every possible direction with equal probability. But now imagine that the flowers have a very slight tendency to face the same direction, maybe because of a prevailing wind, or the angle of sunlight, or some subtle environmental factor. From far away, you might not notice it. But if you measured carefully, you'd find that slightly more flowers face north than south, or east than west. That's what we're seeing with galaxies. A whisper of alignment, a gentle bias, a cosmic breeze perhaps, blowing through the structure of space itself. Now let's pause and think about what this means. Because finding aligned galaxy spins is different from finding an axis in the CMB, even though both are pointing toward the same unsettling conclusion. The universe might have a preferred direction. The CMB axis is imprinted in the oldest light in the universe. It's a pattern from the Big Bang, frozen in place when the universe was just 380,000 years old. If that axis is real, it suggests that the initial conditions of the universe, the distribution of matter and energy at the very beginning, were not perfectly isotropic. Aligned galaxy spins, on the other hand, formed much later. Galaxies began forming a few 100 million years after the Big Bang and continued forming for billions of years. Their spins are determined by the flow of matter during galaxy formation, by mergers and interactions, by the gravitational pull of surrounding structures. If galaxy spins are aligned, it could mean that large-scale flows of matter in the universe have a preferred direction. It could mean that the web-like structure of the cosmos, the filaments of galaxies stretching between vast voids, is not randomly oriented but organized around some underlying symmetry. Or it could mean something even stranger. It could mean that space itself has a twist to it, a rotation, a handedness built into the geometry of the universe. There's a concept in cosmology called a rotating universe. It sounds like science fiction, but it's actually a legitimate solution to Einstein's equations. In 1949, the mathematician Kurt Gödel, famous for his incompleteness theorems in logic, found a solution to general relativity that described a universe filled with matter that was rotating. Not individual galaxies rotating, but the entire universe spinning as a single entity, space and time twisted together in a cosmic vortex. Gödel's universe was bizarre. In it, you could travel forward in time by moving through space. Causality became strange and loopy. Most physicists dismissed it as a mathematical curiosity, not a description of our actual universe. But what if our universe has just a tiny amount of rotation? Not enough to create time travel paradoxes or violate causality, but enough to leave subtle traces in the alignments of galaxies and the patterns of the CMB. The idea is speculative, of course. There's no direct evidence for a rotating universe, but it's one of the possibilities that the data keeps whispering about. Late at night, when scientists are staring at their computer screens and wondering if they're seeing something real or just chasing shadows. Let's consider another piece of this puzzle: quasars. These are among the brightest and most distant objects in the universe, powered by supermassive black holes at the centers of young galaxies. As matter spirals into a quasar's black hole, it heats up to millions of degrees and emits tremendous amounts of light across the entire electromagnetic spectrum. Quasars are useful for studying the universe because they're so bright. We can see them across vast distances, looking back in time to when the universe was much younger. And because they're associated with black holes, they have strong magnetic fields and emit polarized light waves that oscillate in a particular direction. In 2014, a team of astronomers led by Damian Hutzemeckers analyzed the polarization of light from 355 quasars spread across a large region of the sky. They found something remarkable. The polarization axes, the directions in which the light waves were oscillating, were not randomly oriented. They were aligned with each other over enormous distances, across billions of light years. This alignment correlated with the large-scale structure of the universe in that region. Quasars located along the same cosmic filaments tended to have similar polarization angles. It was as if the magnetic fields around these quasars were being influenced by some larger-scale magnetic field threading through the cosmic web. But even more intriguingly, when the team extended their analysis to include quasars from other parts of the sky, they found hints that the alignment wasn't just local. There seemed to be a large-scale pattern, a preferred orientation, that spanned a significant fraction of the observable universe. This was controversial. Other teams tried to replicate the findings with different data sets and different analysis methods. Some confirmed the alignment. Others found it was weaker than initially claimed, or that it vanished when you accounted for certain observational biases. The debate continues, but the tantalizing possibility remains. Quasar polarization might be tracing out a cosmic magnetic field or a large-scale structure in space that has a preferred orientation. And that orientation might align with the axis of evil in the CMB and the spin directions of distant galaxies. Are you seeing the pattern yet? Separate lines of evidence, each one tentative and uncertain on its own, but all pointing in the same unsettling direction. The CMB with its anomalous axis. Galaxy spins with their weak but persistent alignment. Quasar polarization with its hints of large-scale order. It's like hearing the same melody played on different instruments, each one slightly out of tune, but all recognizably the same song. You can't quite make out the lyrics, you can't identify the composer, but you know there's music playing, faint and far away, just beyond the edge of hearing. Of course, we must be careful. Science is full of examples where apparent patterns turned out to be nothing. Artifacts of incomplete data, flaws in analysis, or simple coincidence. The human mind is exquisitely good at finding patterns, even where none exist. We see faces in clouds, hear words in static, find meaning in randomness. That's why astronomers are cautious. That's why these findings have been debated for years without consensus. That's why even mentioning the axis of evil can make some scientists uncomfortable, as if naming it gives it more reality than it deserves. But the data persists. And as our telescopes get better, as our surveys get larger, as our analysis methods become more sophisticated, the whispers don't fade. They remain. Quiet, consistent, patient. And that brings us to an important question. One we'll explore more deeply as this gentle night unfolds. If the universe does have a preferred direction, what could cause it? What mechanisms, what processes, what fundamental features of reality could produce such an alignment? There are several possibilities, each with its own implications for cosmology and physics. Some are modifications to our understanding of the Big Bang. Some involve new fields or forces pervading space. Some require rethinking the geometry of the universe itself. We'll examine these ideas carefully, one by one, with no rush. For now, just let the strangeness settle over you like a soft blanket. The universe might be spinning. Everything might be organized around a hidden axis, a cosmic pole star that doesn't shine with light, but with pure geometry. It's a beautiful thought, in its own peculiar way. The idea that beneath all the chaos and randomness of stars and galaxies, there's a subtle order, a direction, a meaning woven into the structure of space itself. Whether it's true or not, we don't yet know. But the possibility alone is enough to make you look up at the night sky differently. To wonder if, when you gaze out at the stars, you're not just seeing random lights scattered across darkness, but part of a grand pattern, turning slowly around an axis billions of light years long. Rest your eyes for a moment. Let your breathing slow. We're building a picture here, piece by piece, like assembling a puzzle in dim light. Each piece adds a little more detail, a little more context, bringing us closer to understanding what this cosmic axis might mean, or whether it means anything at all. We have more to explore, more evidence to examine, more mysteries to unravel. But we're taking our time, because the universe has been here for 13.8 billion years, and it's not going anywhere soon. Neither are we. Let's drift now into a different kind of thinking. Let's talk about space itself, not the space between stars. That's just emptiness, or mostly emptiness. But space as a thing, as a physical entity with properties and structure. Space as something that can bend, twist, stretch, and curve. This is where Einstein comes in naturally. With his wild hair and his thought experiments and his ability to see the universe in ways no one had before, Einstein taught us that space and time are not separate. They're woven together into a single fabric called spacetime, and that fabric can be shaped by matter and energy. Imagine a trampoline. When it's empty, the surface is flat, but place a bowling ball in the center and the fabric sags, creating a dip. That dip is curvature, and if you roll a marble across the trampoline, it will curve toward the bowling ball, not because there's a force pulling it, but because it's following the natural contours of the curved surface. That's how gravity works in Einstein's general relativity. Mass and energy curve space-time, and objects move along the curved paths, the geodesics, that represent the straightest possible lines through that curved space. There's no force pulling things together, there's just geometry. This insight revolutionized physics, but it also opened up fascinating questions about the shape of the universe itself. Because if mass curves space-time locally around stars and planets and galaxies, then what about all the mass in the universe combined? How does the entire cosmos curve space on the largest scales? The standard model of cosmology assumes the universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere, no special locations. Isotropic means the same in all directions, no special orientations. Together, these assumptions imply that the universe has a simple, highly symmetrical geometry. There are three basic possibilities for the overall shape of space, depending on how much matter and energy the universe contains. The universe could be flat, like an infinite sheet of paper. It could be positively curved, like the surface of a sphere. Or it could be negatively curved, like a saddle or a Pringle chip. Measurements of the CMB and other cosmological data tell us that our universe is very close to flat. Not perfectly flat, we can't measure with infinite precision, but flat enough that if there's any curvature, it's extremely gentle, stretching across distances far larger than the observable universe. A flat universe is special. It represents a precise balance between expansion and gravity, like a ball thrown upward at exactly the escape velocity. Any faster and it would escape forever. Any slower and it would fall back. Our universe sits right on that knife edge, expanding but not accelerating away. Except it is accelerating because of dark energy, but that's another layer of strangeness we'll touch on later. But here's the thing. Even in a flat universe, there can be twists. There can be orientations. The universe could be flat on average, but still have anisotropies, variations from place to place or direction to direction. And if the universe has a preferred direction, that's a kind of anisotropy. So when we find hints of an axis in the CMB, or aligned galaxy spins, we're potentially seeing evidence that the universe's geometry is not perfectly isotropic. That space itself might have a subtle handedness, a twist, a directionality built into its structure. One way this could happen is if the universe is rotating. We mentioned Kurt Gödel's rotating universe earlier, but there are other, less extreme versions of rotation that could occur without creating causality problems. The universe could have a small, primordial rotation, a legacy from whatever process gave birth to the Big Bang, that leaves traces in the alignments we observe today. If the universe is rotating, even slowly, it would create a preferred axis, the axis of rotation. Things would tend to spin in a coordinated way around that axis. Large-scale flows of matter would have vorticity, a technical term for the tendency to swirl. And patterns in the CMB might reflect the twisted geometry of a rotating spacetime. But measuring the rotation of the universe is extraordinarily difficult. You can't just stand outside and watch it spin. You're inside it, rotating with it, and everything you see is filtered through your own motion. It's like trying to measure the rotation of a merry-go-round while you're sitting on one of the horses. Astronomers have tried, though. They've looked for systematic patterns in the velocities of galaxies, searching for evidence of large-scale vorticity. They've analyzed the polarization of the CMB, which would be affected by rotation. They've studied the spins of galaxies, as we discussed earlier, looking for correlated alignments. The results are intriguing, but not conclusive. Most studies find that if the universe is rotating, it's doing so very slowly, far too slowly to be directly observable with current technology. But the upper limits keep getting tighter as our measurements improve, and some studies hint at non-zero rotation rates that are just barely allowed by the data. It's a bit like listening for a very faint sound in a noisy room. You're not sure if you're hearing something real or just the random fluctuations of background noise. But you keep listening, keep refining your instruments, keep hoping that if you're patient enough, the signal will become clear. Another possibility is that the universe has a more exotic geometry than we typically assume. What if space is not simply connected? What if the universe wraps around on itself in strange ways, creating topologies that are finite but have no boundaries? Imagine living on the surface of a torus, a donut shape. If you walk far enough in any direction, you'll eventually come back to where you started. The surface is finite, but there are no edges. It loops back on itself, and depending on how the torus is oriented, there could be preferred directions, around the donut's major axis or around its minor axis. Our three-dimensional universe could have a similar topology. It could be a three-dimensional torus, or some other exotic shape like a Poincare dodecahedral space or a Klein bottle. These shapes are hard to visualize, impossible to fully picture really, because they exist in dimensions our brains aren't wired to comprehend, but they're mathematically well-defined and perfectly legitimate solutions to Einstein's equations. If the universe has one of these exotic topologies, it could create patterns in the CMB. Light traveling around the universe in different directions might interfere with itself in subtle ways, creating alignments or correlations that wouldn't exist in a simply connected space. Some researchers have searched for these signatures, matching circles in the CMB, where light from the same source has traveled around the universe via different paths. But so far, nothing definitive has been found. Still, the possibility remains. The universe's geometry might be far stranger than the simple flat expanse we imagine. And that strangeness might be responsible for the anomalies we're seeing. There's another concept worth mentioning here: cosmic inflation. Inflation is the idea that the very early universe underwent a brief period of exponential expansion, growing from something smaller than an atom to something larger than a galaxy in a tiny fraction of a second. This rapid expansion would have smoothed out the universe, erasing most irregularities and creating the large-scale uniformity we observe. Inflation is the leading explanation for why the CMB is so uniform. But inflation isn't a single, well-defined theory. It's more like a family of related ideas, each with different details about what drove the expansion and how it ended. And in some versions of inflation, the process could leave behind anisotropies, preferred directions imprinted in the fabric of space. For example, if the field driving inflation, called the inflaton field, had a direction associated with it, like an arrow pointing through space, that direction would be preserved as a feature of spacetime even after inflation ended. It would create an axis, a preferred orientation, a cosmic memory of the universe's violent birth. This is speculative, of course. Most simple models of inflation predict an isotropic universe, but more complex models, with multiple fields or unusual dynamics, can produce anisotropies. And as we learn more about inflation, if indeed it happened at all, we might find that our universe's geometry carries scars from that earliest epoch, visible now only as the faintest alignments in ancient light. Let's think about this in a different way. Let's think about symmetry. Symmetry is one of the most powerful concepts in physics. When something has symmetry, it means it looks the same after certain transformations. A sphere has perfect rotational symmetry. Spin it any way you like, and it looks identical. A snowflake has six-fold rotational symmetry. Turn it by 60 degrees, and you can't tell it's been rotated. The laws of physics have deep symmetries. They're the same here on Earth as they are in distant galaxies. They're the same today as they were billions of years ago. These symmetries lead to conservation laws. Conservation of energy comes from time symmetry. Conservation of momentum from space symmetry. The cosmological principle, the assumption that the universe is isotropic, is essentially a statement about symmetry. It says the universe has rotational symmetry. There's no preferred direction. And from this symmetry, we derive many of our conclusions about how the universe works. But what if that symmetry is broken? What if the universe only appears isotropic when you don't look carefully enough, but reveals subtle asymmetries when you examine it with precision instruments? Symmetry breaking is common in physics. Water has perfect symmetry, molecules moving randomly in all directions. But when water freezes into ice, that symmetry breaks. Ice crystals have a structure, a preferred orientation. The molecules arrange themselves in hexagonal patterns, choosing one configuration out of infinitely many possible ones. Could something similar have happened to the universe? Could space itself have undergone a phase transition, like water freezing, that broke its perfect symmetry and left behind a preferred direction? This idea connects to something called spontaneous symmetry breaking, a concept that's central to our understanding of particle physics and the Standard Model. The Higgs field, which gives particles their mass, is an example. In the very early universe, the Higgs field was symmetrical. But as the universe cooled, the field settled into a particular configuration, breaking that symmetry and giving different particles different masses. If a similar process affected the geometry of space itself, it could create anisotropies. A cosmic phase transition could have chosen a particular direction, the way a magnetizing piece of iron chooses a particular axis for its magnetic field. And that direction would be preserved as a feature of space-time, visible now in the patterns of the CMB and the alignments of galaxies. These are deep ideas, abstract ideas, ideas that take us far from everyday experience into realms where mathematics is the only reliable guide. But they're also strangely beautiful in the way that theoretical physics can be. They suggest that the universe has a history written in its geometry, that space itself remembers where it came from. Now, let's bring this back to something more tangible. Let's talk about what we can actually observe. When astronomers map the large-scale structure of the universe, the distribution of galaxies across cosmic distances, they find a pattern often called the cosmic web. Galaxies aren't scattered randomly through space. They're organized into filaments, long threads of matter stretching between enormous voids. Where filaments intersect, you find clusters of galaxies, some containing thousands of individual galaxies bound together by gravity. This web-like structure formed over billions of years as gravity pulled matter together. Dense regions became denser, attracting more matter. Underdense regions became emptier as matter flowed away toward the denser areas. The result is a foamy, filamentary structure that fills the entire observable universe. In a perfectly isotropic universe, this cosmic web would have no preferred orientation. The filaments would point in all directions equally. If you measured the orientations of galaxy clusters or the directions of filaments, you'd find random distributions. But several studies have found hints, always hints, never certainties, that the cosmic web might have large-scale alignments. Filaments in one region of space seem to point in similar directions. Galaxy clusters seem to be elongated along axes that correlate with each other across vast distances. One study from 2016 analyzed the shapes of over 1 million galaxies from the Sloan Digital Sky Survey. By measuring how galaxies were elongated and oriented, the researchers could infer the directions of the filaments they belonged to. And they found a surprising pattern. The orientations were correlated across scales larger than 100 million light-years. This doesn't mean all filaments point the same way, but it means there's less randomness than expected. There's a subtle bias, a gentle preference, a whisper of order amid the chaos. Imagine a forest where the trees grow in random directions. But when you map the entire forest, you notice that trees on the eastern side tend to lean slightly eastward, and trees on the western side tend to lean slightly westward, as if the whole forest is being shaped by some large-scale pattern in the soil or prevailing winds. That's analogous to what we might be seeing in the cosmic web. What could cause such large-scale alignments? One possibility is tidal forces, gravitational tugs, from even larger structures beyond our observable horizon. If there's matter outside what we can see, its gravity would still affect the motion of matter near the edge of our observable universe. Those tidal forces could create flows and alignments that extend inward, organizing the cosmic web in subtle ways. Another possibility is primordial velocity fields, large-scale motions of matter imprinted during the Big Bang or inflation. If the early universe had small velocities with a preferred direction, those velocities would grow along with the universe, eventually shaping how galaxies and filaments form. The cosmic web would inherit the orientation of those primordial flows, preserving them like a fossil record in stone. Or perhaps the alignment is connected to magnetic fields. The universe is threaded with weak magnetic fields, generated by moving charged particles in galaxies and galaxy clusters. These fields are generally tangled and chaotic, but there might be large-scale components, coherent magnetic fields stretching across cosmic filaments that help organize matter and create alignments. Each of these explanations has problems. Each requires certain conditions that we're not sure exist. But they're all plausible, all worth investigating, all potentially pieces of the puzzle we're slowly assembling. And that brings us to an important point, one worth pausing to consider. Science doesn't progress by finding definitive answers overnight. It progresses by accumulating evidence, testing hypotheses, ruling out possibilities, and gradually narrowing down the range of what might be true. It's a slow process, a patient process, sometimes frustratingly uncertain, but that's also what makes it robust. Science doesn't leap to conclusions. It waits. It checks. It demands reproducibility and rigor. And when something surprising appears, like an axis in the CMB or aligned galaxy spins, the scientific community approaches it with a mix of curiosity and skepticism, eager to understand but cautious about being fooled. So when we talk about a hidden axis of the universe, we're not making a bold claim. We're exploring a possibility. We're following a thread of evidence that might lead somewhere fascinating or might ultimately unravel into nothing. We don't know yet. And that's okay. That's how discovery works. Let your mind rest for a moment. We've covered a lot of ground, from the geometry of spacetime to the structure of the cosmic web, from inflation to symmetry breaking. These ideas connect in subtle ways, each one adding context to the others, building a picture of a universe that might be more interesting than we thought. The universe might have a shape, not in the sense of an outline or a boundary. It could be infinite, extending forever in all directions. But a shape in the sense of geometry, of curvature, of preferred directions, woven into the fabric of space itself. A shape that influences how matter moves, how galaxies align, how light travels across billions of years. And if that's true, then we're not just living in a universe. We're living in a universe with character, with history, with features that trace back to its earliest moments. We're living in a cosmos that remembers where it came from, even if those memories are written in a language we're only beginning to read. That's a profound thought, and it's worth sitting with for a while, letting it settle into your awareness like sediment drifting to the bottom of a still pond. We'll continue exploring this mystery as the night unfolds. There are more clues to examine, more patterns to consider, more questions to ask. But for now, just breathe. Let your body relax. Let these ideas float through your consciousness, like stars drifting across the sky, each one brilliant and distant and connected to all the others in ways you can feel but not quite articulate. The universe is vast, but it's also intimate, because you're part of it, made of the same atoms, shaped by the same forces, embedded in the same cosmic web. When you look up at the night sky, you're not looking at something separate from yourself. You're looking at your extended body, your cosmic home, the vast structure of space and time in which your small life unfolds. And maybe, just maybe, that structure has an axis, a direction, a subtle orientation that connects you to the furthest galaxies and the oldest light, a thread running through everything, invisible but real, waiting to be discovered. We're getting there, slowly, gently, one quiet thought at a time. Now we return to where this story began, the cosmic microwave background, that faint, all-encompassing glow that fills the universe, the afterglow of creation, the oldest light we can see. We've talked about the CMB before, but now we're going to look more closely at its patterns. Because hidden in those patterns, in the tiny temperature variations across the sky, is information about the universe's structure, history, and perhaps its deepest symmetries. When you look at a map of the CMB, you see spots of different colors representing slightly warmer and cooler regions. The temperature differences are minuscule, just a few hundred thousandths of a degree, but they're real and they're important. These temperature variations reflect density variations in the early universe. Where the CMB is slightly warmer, matter was slightly denser. Where it's cooler, matter was slightly less dense. Those density variations eventually grew into galaxies. The small overdensities attracted more matter through gravity, getting denser and denser over billions of years until stars ignited and galaxies formed. The CMB is a baby picture of the universe, and if you look carefully, you can see the hints of everything that would come later. But scientists don't just look at the CMB map visually, they analyze it mathematically, breaking it down into components at different angular scales using spherical harmonics, as we mentioned before. This mathematical decomposition reveals patterns that would be invisible to the eye. And it's in those mathematical patterns, particularly in the lowest multipole moments, the largest scale features, that the axis of evil appears. Let's explore exactly what that means, gently and carefully. The monopole, the zeroth moment, represents the average temperature of the entire CMB. It's uniform across the whole sky, about 2.7 Kelvin or 2.7 degrees above absolute zero. This tells us the average temperature of the universe today, cooled by expansion from its much hotter beginnings. The dipole, the first moment, represents a pattern where one half of the sky is slightly warmer and the other half is slightly cooler. In our universe, the CMB has a strong dipole. This dipole is caused by our motion through space. The Milky Way, along with our local group of galaxies, is moving at about 600 kilometers per second relative to the CMB rest frame. Because of the Doppler effect, the CMB appears slightly warmer in the direction we're moving toward and slightly cooler in the direction we're moving away from. This dipole is well understood and expected. Scientists subtract it from the data when analyzing the CMB's deeper patterns because it tells us about our motion, not about the universe's structure. But then come the quadrupole and octopole. The quadrupole, the second moment, divides the sky into 4 regions, alternating hot and cold. The octopole, the third moment, divides it into 8. These patterns should reflect the density variations in the early universe, and their orientations should be random or at least uncorrelated. But they're not. They're aligned. The quadrupole's axis and the octopole's axis point in nearly the same direction. This alignment is unlikely to happen by chance, though not impossible. And more strangely, both axes seem to correlate with features of our local environment, the ecliptic plane and the Earth's equator. This is the axis of evil. And it's been confirmed by multiple satellites, COBE, WMAP, and Planck. Each time scientists hoped it would go away. Each time it persisted. Why is this so troubling? Because the CMB comes from 380,000 years after the Big Bang, from a region of space now stretched across the entire observable universe. The photons that form the CMB were emitted from points, billions of light years apart, so far apart that they couldn't have communicated with each other, couldn't have coordinated their temperatures or patterns. They're causally disconnected, separated by more space than light could have crossed in the age of the universe. So how could they conspire to create patterns that align with the ecliptic plane of our solar system, which didn't even exist yet? How could the universe 380,000 years after the Big Bang know about the orientation of a small rocky planet that wouldn't form for another 9 billion years? The answer, of course, is that it couldn't. The universe doesn't know about Earth. It doesn't care about our solar system. So if there's an alignment between the CMB and the ecliptic, either it's a coincidence, unlikely but possible, or there's some systematic error in our measurements that creates a false pattern. Scientists have examined both possibilities exhaustively. They've looked for instrumental effects, for contamination from our galaxy, for subtle calibration issues. The Planck team, in particular, spent years trying to explain the axis away. They tested dozens of alternative explanations, checking whether dust in the Milky Way might create patterns that mimic the axis, whether radio emission from our galaxy might interfere with the measurements, whether the satellite's instruments had any directional biases. They found some foreground contamination, emission from our galaxy that had to be carefully subtracted. But even after removing every known source of contamination, the axis remained. Weaker, perhaps, but still there, still aligned, still significant at about the 99% confidence level, meaning there's only a 1% chance it's pure random coincidence. That's not enough to be certain. In science, especially cosmology, we usually demand higher confidence, 99.7% or better, sometimes called 5 sigma significance. The CMB axis doesn't quite reach that threshold. It's more like 3 sigma, which is intriguing but not definitive. But here's what makes it more compelling. It's not just the axis. There are other anomalies in the CMB, other patterns that shouldn't exist. Let's talk about those. One anomaly is the cold spot. This is a region of the CMB that's much colder than the surrounding areas. About 70 microkelvins colder, which doesn't sound like much, but is huge by CMB standards. It's located in the southern celestial hemisphere, in the direction of the constellation Eridanus. The cold spot is unusual not just because it's cold, but because it's large. It spans about 5 degrees across the sky, roughly 10 times the diameter of the full moon. Features this large in the CMB should be rare. There should only be a few of them in the entire sky, and they should have a certain expected amplitude. The cold spot exceeds that expected amplitude. It's an outlier. Some scientists have suggested the cold spot might be caused by a supervoid, an enormous empty region of space between us and the surface of last scattering where the CMB originates. Photons traveling through a supervoid would lose energy and arrive at a slightly cooler, a phenomenon called the integrated Sachs-Wolf effect. And indeed, there is a supervoid in that direction, detected through galaxy surveys. But the void isn't quite large enough to explain the full amplitude of the cold spot. There's still a deficit, a missing piece of the explanation. Some researchers have proposed that the cold spot might be evidence of exotic physics, perhaps a collision with another universe, or a texture in spacetime, or some other phenomenon from the very early universe. Or it might just be a statistical fluke. With enough features in the CMB, some of them will be extreme outliers just by chance. The cold spot might be one of those chance events that looks meaningful but isn't. Still, it's interesting that the cold spot lies roughly along the axis defined by the quadrupole and octopole alignment. It's as if all these anomalies are connected, parts of a larger pattern we're only beginning to discern. Another anomaly is the lack of large-scale power. When scientists analyze the CMB's multipole moments, they can calculate how much power, how much temperature variation, exists at each angular scale. You'd expect a certain amount of power at large scales, based on models of how density variations grew in the early universe, but the observed CMB has less power at large scales than predicted. The quadrupole, in particular, has only about half the expected amplitude. This deficit has been confirmed by all 3 CMB satellites. It's real, not an artifact. What does it mean? One possibility is that the universe is finite, smaller than the observable horizon, and wraps around on itself. If space has a topology that creates a maximum wavelength for variations, you'd see a cutoff in power at large scales. The CMB would have a minimum feature size, determined by the universe's overall shape. But if the universe is finite, it should have left other signatures in the CMB, patterns or correlations that haven't been clearly detected. So this explanation remains uncertain. Another possibility is that inflation, the rapid expansion of the very early universe, ended in a particular way that suppressed large-scale fluctuations. Different models of inflation make different predictions about the spectrum of density variations. Maybe the universe chose a version of inflation that produces less power at large scales. Or maybe the deficit is connected to the axis. Maybe the alignment of the quadrupole and octopole is not just a directional anomaly, but also an amplitude anomaly. Maybe whatever process created the preferred direction also reduced the overall power at large scales. These ideas are speculative, each one requiring further evidence to be taken seriously. But they illustrate how the anomalies in the CMB might be interconnected, pieces of a puzzle that fit together in ways we haven't yet figured out. There's also an asymmetry between the northern and southern hemispheres of the CMB. When scientists analyze the 2 halves of the sky separately, they find that one hemisphere has slightly more temperature variation than the other. This asymmetry, called the hemispherical power asymmetry, is subtle but statistically significant. In a perfectly isotropic universe, the 2 hemispheres should have identical statistics. Any difference should be pure noise, averaging to 0. But the observed asymmetry persists across different multipole ranges and different ways of dividing the sky. It's real. This asymmetry could be caused by a large-scale gradient in the density of the early universe. Perhaps one side of the observable universe had slightly more matter than the other side. Or perhaps there was a primordial magnetic field, or some other field with a gradient, affecting how matter clumped together. Or perhaps, and this is where things get really interesting, the asymmetry reflects the fact that we're not at the center of a symmetric universe. Maybe we're off to one side of a larger structure, seeing an asymmetric view because of our location. Imagine you're standing in a forest. If you're in the exact center, the forest looks the same in all directions. But if you're near the edge, you see more trees on one side and fewer on the other. An observer in a different location would see a different asymmetry. Could the CMB's hemispherical asymmetry mean we're near the edge of something? Perhaps the edge of the region affected by inflation, or the edge of a finite universe, or the boundary of some large-scale structure that extends beyond our observable horizon. These questions don't have answers yet. They're still in the realm of speculation, guided by data, but not yet constrained enough to reach firm conclusions. But they point toward a theme that runs through all these anomalies. The universe might be more complex, more structured, more interesting than the simple isotropic models we've been using for decades. And all of these anomalies, the axis of evil, the cold spot, the lack of large-scale power, the hemispherical asymmetry, could be related. They could be different manifestations of the same underlying phenomenon, different ways that a preferred direction or a broken symmetry leaves its mark on the oldest light in the universe. Or they could be unrelated, separate coincidences that happen to appear in the same dataset. Science can't yet distinguish between these possibilities with certainty. We need more data, better models, deeper understanding. But the persistence of these patterns across multiple satellites and multiple analysis methods suggests they're telling us something real, something about the universe's geometry, or its initial conditions, or the processes that shaped it in its earliest moments. Let's pause here and take a breath. We've been diving deep into technicalities, multipole moments and power spectra and hemispherical asymmetries. These are abstract concepts, mathematical descriptions of patterns in data. It's easy to get lost in the details and lose sight of the bigger picture. So let's step back. Let's remember what we're really talking about. We're talking about light that's been traveling for 13.8 billion years. Light that was emitted when the universe was just a fraction of its current age, when no stars had yet formed, when matter was just beginning to clump together into the structures we see today. That light carries information. It's a message from the past, written in the language of temperature variations and polarization patterns. And encoded in that message might be clues about the universe's deepest properties, its shape, its history, its fundamental symmetries. When we find anomalies in that message, it's like finding unexpected words in an ancient text. They might be errors, misinterpretations, artifacts of how we're reading the text. Or they might be genuine, revealing something the authors wanted to convey, something we hadn't anticipated finding. The axis of evil and its companion anomalies are those unexpected words, and scientists are still trying to decide whether they're meaningful or not, whether they're telling us the universe has a preferred direction, or whether they're just noise, coincidence, illusion. The answer matters, because if the universe truly has an axis, it changes how we think about cosmology. It suggests that the Big Bang wasn't perfectly symmetric. That space itself might have structure we haven't accounted for, that our models need revision, refinement, expansion to accommodate new truths. But even if the axis turns out to be nothing, a statistical fluke that fooled multiple generations of scientists, the process of investigating it is valuable. Science progresses not just by finding answers, but by asking better questions. And the axis of evil has certainly led to better questions about isotropy, about symmetry, about what we can infer from the patterns we observe. So whether it's real or not, the axis has already done its job. It's pushed us to look more carefully, think more deeply, question our assumptions. It's reminded us that the universe doesn't owe us simplicity, that nature might be more subtle, more complex, more beautifully strange than our theories predict. And that's exciting, That's why scientists keep searching, keep analyzing, keep trying to understand these faint patterns in ancient light. Because somewhere in those patterns, there might be truth, new truth, surprising truth, the kind of truth that reshapes how we see reality. Your eyes are probably getting heavy now. Your mind is drifting, following these ideas like following a stream through a forest, not sure where it leads, but enjoying the journey anyway. That's perfect. That's exactly where you should be. Relaxed, curious, open to wonder, but not straining to grasp every detail. Let the CMB wash over you like its photons have, washed over the Earth for billions of years, invisible and silent and patient. Let the anomalies be what they are, mysteries, possibilities, invitations to keep exploring. We're going to continue this journey. There's more to discover, but we're taking our time, letting each piece of the puzzle settle into place before we move to the next one. Because the universe isn't in a hurry, and neither are we. Just drift. Just listen. Just let these cosmic whispers carry you deeper into the night, where science and wonder and the quiet peace of not knowing all the answers blend together into something that feels almost like dreaming. Let's turn our attention now away from ancient light and toward the structures that light illuminates. Let's talk about galaxies, not as individuals, but as a collective. As a vast population spread across space and time, each one spinning, each one shaped by forces both local and cosmic. Galaxies are beautiful. If you've ever seen pictures from the Hubble Space Telescope or the James Webb Space Telescope, you know what I mean. Spirals with graceful arms sweeping through space. Ellipticals that glow with the soft light of 1 trillion old stars. Irregulars that look chaotic, torn apart by interactions with neighbors or recently formed from colliding gas clouds. Each galaxy is unique, but galaxies also follow patterns. They come in distinct types. They have characteristic sizes, masses, colors. They're not randomly distributed through space, but organized into groups, clusters, and superclusters connected by the cosmic web we discussed earlier. And as we've touched on before, galaxies spin. They rotate, and the directions of those spins might not be as random as we once thought. Let's go back to that 2011 study by Michael Longo. Longo analyzed images of spiral galaxies from the Sloan Digital Sky Survey, focusing on galaxies that were oriented face-on or nearly face-on, so their spiral structure was clearly visible. He classified each galaxy as either left-handed or right-handed, based on the direction its spiral arms wound outward. This is trickier than it sounds. Spiral arms aren't like solid objects with a clear rotation. They're density waves, regions where stars and gas happen to pile up temporarily as they orbit the galactic center. It's a bit like traffic jams on a highway. The cars are moving, but the jam itself stays in one place, or moves slowly compared to the individual cars. Spiral arms work the same way, but you can still determine the direction of rotation by looking at which way the arms trail. Imagine a rotating lawn sprinkler. The water sprays outward, but because the sprinkler is spinning, the water forms curved arcs that trail behind the rotation. Spiral arms trail in the same way. Longo classified tens of thousands of galaxies and found that slight but statistically significant excess of left-handed spirals in the northern galactic hemisphere and right-handed spirals in the southern hemisphere. The effect was weak, only about a 7% difference from the expected 50-50 split. But it was consistent across different subsamples of the data. If real, this would be remarkable. It would suggest that galaxies across huge volumes of space have correlated spins, all organized around the same axis. And that axis would be aligned with the Milky Way's own rotation axis, which is deeply puzzling because our galaxy is just one among billions, with no special status in the cosmos. Other researchers tried to replicate Longo's findings. Some succeeded, finding similar patterns in different data sets. Others found no significant effect, or found patterns that pointed in different directions. The debate became complex, mired in questions about methodology, sample selection, and the difficulty of determining galaxy spins from two-dimensional images. But the idea wouldn't go away, because even if Longo's specific result was questionable, the underlying question remained fascinating. Do galaxy spins have large-scale alignments? In 2020, a study took a different approach. Instead of classifying spiral arms visually, researchers used automated algorithms to measure the three-dimensional shapes and orientations of hundreds of thousands of galaxies. They analyzed data from multiple sky surveys, cross-checking results to minimize systematic errors, and they found something. Not exactly what Longo found, but something related. Galaxy spin axes showed weak but statistically significant correlations over scales of hundreds of millions of light-years. Galaxies in the same large-scale structure, the same cosmic filament or supercluster, tended to have spins that were more aligned than you'd expect from chance. This makes some physical sense. When galaxies form within the same filament, they're all influenced by the same large-scale flows of matter. Matter spiraling down the filament has a net angular momentum, and galaxies forming from that matter inherit that spin. So you'd expect galaxies in the same filament to have correlated orientations. But the correlations seem to extend beyond individual filaments. They seem to span multiple filaments, suggesting an even larger scale pattern in the angular momentum of the universe. Other studies found similar results using different methods. One analyzed the orientations of galaxy clusters, not the individual galaxies, but the overall shapes of the clusters themselves. Clusters are often elongated, shaped like footballs or cigars, rather than perfect spheres. And the directions of those elongations showed correlations across vast distances. Another study looked at the spins of smaller substructures within galaxy clusters. Each cluster contains smaller groups of galaxies, orbiting within the cluster's gravitational field. Those orbits have orientations. Some groups circle clockwise, others counterclockwise, and the distribution of orbital orientations showed patterns that aligned with the cluster's surroundings, with the cosmic web's local structure, and possibly with even larger scales beyond. All of these findings are subtle. None of them show perfect alignment, where every galaxy or cluster points the same way. Instead, they show statistical tendencies, slight biases, patterns that only emerge when you analyze thousands or millions of objects together. It's like measuring the alignment of trees in a forest. If you look at one tree, it's pointing in some random direction. Look at 10 trees, still random. But look at 10,000 trees, and you might notice that 51% point within 30 degrees of north, while only 49% point within 30 degrees of south. That 2% difference, tiny for any individual tree, becomes statistically significant when measured across the whole forest. That's what we're seeing with galaxies. Small biases, gentle preferences, whispers of order beneath the apparent randomness. Why does this matter? Because if galaxy spins are aligned across cosmic scales, it tells us something about the initial conditions of the universe. It tells us that the distribution of angular momentum, the spin, wasn't random. There was structure. There was coherence. There was perhaps a preferred direction built into the primordial universe, preserved and amplified as galaxies formed. And that preferred direction might be the same axis we see in the CMB. The axis of evil might not just be a pattern in ancient light. It might be a feature of the universe's angular momentum field, visible both in the CMB's temperature variations and in the spins of galaxies that formed billions of years later. Imagine the universe as a vast ocean. The CMB is like the surface of that ocean, reflecting light from the sky above. The galaxies are like eddies and whirlpools in the ocean's depths. If the ocean has a current, a large-scale flow, both the surface patterns and the deep eddies would be affected by it. They'd show correlations, alignments, evidence of the underlying current, even if you couldn't see the current directly. The universe might have such a current, a cosmic vorticity, a large-scale twist to space itself. And we're seeing its effects in multiple independent ways, in the CMB, in galaxy spins, in the structure of the cosmic web, in the orientations of clusters and filaments. Or maybe not. Maybe these correlations are just coincidences. Maybe they're artifacts of how we measure things, or selection effects in our data, or subtle biases we haven't identified yet. Science is full of patterns that seemed real but turned out to be illusions. But the fact that multiple independent lines of evidence are pointing in the same direction is suggestive. It's not proof, but it's a hint, a clue, a thread worth following to see where it leads. Let's talk about another kind of alignment: the orientations of radio jets from active galactic nuclei. These are some of the most energetic phenomena in the universe, powered by supermassive black holes at the centers of galaxies. As matter spirals into the black hole, it forms an accretion disk, a swirling disk of superheated gas and plasma. Magnetic fields threading through this disk channel some of the infalling material into narrow jets that shoot outward at nearly the speed of light, perpendicular to the disk. These jets can extend for millions of light years, far beyond the galaxy itself. They emit intense radio waves, making them visible to radio telescopes across vast cosmic distances. And because the jets are perpendicular to the accretion disk, their directions tell us about the orientation of the black hole's spin axis. In an isotropic universe, the directions of these jets should be random. Each black hole's spin is determined by the history of matter flowing into it, which should be independent of other black holes far away. But several studies have found that radio jets show weak alignments over large scales, similar to what we see with galaxy spins. One study from 2016 analyzed over 64,000 radio galaxies from a large survey. The researchers measured the position angles of the radio jets on the sky, basically which direction each jet pointed, and they found statistical evidence for large-scale alignments, with jets in certain regions of the sky showing a preference for particular orientations. The effect was weak and only marginally significant, but it was consistent with other findings about galaxy spins and cosmic web orientations. It was another piece of the puzzle, another hint that the universe might have hidden structure in its angular momentum. Another intriguing observation involves the polarization of light from quasars, which we mentioned earlier. Quasars are extremely luminous objects powered by matter falling into supermassive black holes. The light they emit is often polarized, meaning the electromagnetic waves oscillate in a preferred direction rather than randomly. This polarization is created by magnetic fields in the region around the quasar. As light passes through these fields, or is emitted by electrons spiraling in the fields, it picks up a polarization signature. And the direction of polarization tells us about the orientation of the magnetic field. In 2014, Damien Hutzemeckers and his colleagues found that quasar polarization vectors over enormous distances, across billions of light years, showed correlated alignments. Quasars separated by 1 billion light years had polarization angles that were more similar than you'd expect from chance. This suggested that large-scale magnetic fields might thread through the cosmic web, aligning the magnetic fields around individual quasars. And if the universe has a preferred direction, those large-scale fields might be oriented along that axis, creating the correlations we observe. Again, this is controversial. Other studies have tried to replicate the findings with mixed success. Some confirm the alignment, others find it's weaker than initially reported, and still others find no significant effect. The jury is still out, but the pattern is familiar by now. Multiple independent observations, each one uncertain on its own, but all pointing toward the same possibility: large-scale alignments that shouldn't exist in a perfectly isotropic universe. It's like hearing testimony from multiple witnesses. Each witness is unreliable in their own way. Faulty memory, biased perspective, incomplete information. But when all the witnesses tell similar stories, you start to think there might be some truth underlying their accounts, even if you can't fully trust any single testimony. That's where we are with the cosmic axis. Multiple lines of evidence, each one imperfect, but collectively suggestive of something real. Let's think about what it would mean if galaxy spins truly are aligned. What physical mechanisms could create such alignments? One possibility is tidal torques. In the early universe, before galaxies formed, matter was distributed in a web-like pattern with filaments and voids. As regions of overdensity began to collapse under gravity, they were influenced by the tidal gravitational fields from surrounding structures. These tidal fields could exert torques, twisting forces, that gave collapsing regions a net spin. If the tidal fields themselves had a preferred orientation, perhaps because the large-scale density distribution had some anisotropy, then the spins they imparted to forming galaxies would also have a preferred orientation. The result would be correlated galaxy spins across large volumes. This mechanism has been studied in computer simulations. Researchers create virtual universes, starting with initial conditions that mimic the early cosmos, and let gravity shape the evolution over billions of years. In these simulations, tidal torques do indeed create some correlation in galaxy spins, especially for galaxies forming in the same filament or nearby filaments. But the correlations seen in simulations are typically smaller than what some observations suggest. To get strong correlations extending over hundreds of millions of light years, you'd need the initial conditions themselves to have large-scale anisotropies. And that brings us back to the CMB and the possibility that the early universe wasn't perfectly isotropic. Another mechanism involves primordial magnetic fields. If the universe contained weak magnetic fields, even before galaxies formed, perhaps generated during inflation or some phase transition in the very early cosmos, those fields could influence how matter flows and how angular momentum builds up. Magnetic fields can channel plasma flows, creating spiral patterns and imparting spin to collapsing clouds. If there were large-scale coherent magnetic fields threading through the cosmic web, they could create correlated spins across vast distances. And the orientation of those fields might reflect some fundamental feature of the universe's geometry or its initial conditions. We don't know if primordial magnetic fields exist or how strong they might be. Observations of magnetic fields in galaxies and galaxy clusters tell us that fields are ubiquitous. They're everywhere we look, but it's unclear whether these fields were seeded by primordial fields from the early universe, or whether they were generated later by astrophysical processes like supernova explosions and stellar winds. This is an active area of research. Astronomers are trying to measure the faint magnetic fields in intergalactic space, in the voids between galaxies, looking for evidence of primordial magnetism. If found, it would have profound implications not just for galaxy formation, but for our understanding of the universe's earliest moments. There's also the intriguing possibility that the universe itself has a small net rotation. We talked about Kurt Gödel's rotating universe earlier, a solution to Einstein's equations where spacetime itself is spinning. Modern observations rule out the kinds of extreme rotation that Gödel considered. But a tiny amount of rotation, so small it would be almost undetectable, might still be allowed by the data. If the universe is rotating, even imperceptibly, it would create a preferred axis, the axis of rotation, and everything in the universe would be influenced by this rotation, subtly. Galaxy spins would tend to align with the rotation axis. The CMB would show anisotropies related to the twisted geometry of a rotating spacetime. Large-scale flows of matter would have vorticity, a tendency to swirl in a coordinated way. Detecting cosmic rotation is incredibly difficult. You're trying to measure the spin of the entire universe from inside it, which is a bit like trying to determine if a room is rotating while you're sitting in a chair that's bolted to the floor. Everything is rotating together, so you have no fixed reference point. But there are subtle effects that could reveal rotation. The CMB should have specific polarization patterns in a rotating universe. Galaxy spins should show a dipole pattern, more spins aligned one way in one hemisphere of the sky, more the opposite way in the other hemisphere. Gravitational waves propagating through a rotating universe should be affected in characteristic ways. Some studies have claimed to find hints of cosmic rotation in the data. Others have found no evidence and have placed tight upper limits on how fast the universe could be spinning. The current consensus is that if the universe is rotating, it's doing so extraordinarily slowly, far slower than even the orbital period of the Milky Way around the local group. But the possibility remains tantalizing, because even a tiny rotation built into the fabric of space-time itself would be a profound discovery. It would mean the universe has a fundamental directionality, a cosmic spin that was present from the beginning and has been preserved through 13.8 billion years of expansion. Let's take a moment to reflect on how strange and wonderful this all is. We're talking about the possibility that galaxies, enormous islands of stars, each one containing hundreds of billions of suns, might be spinning in a coordinated way across distances so vast that light takes billions of years to cross them. We're talking about patterns in the universe's structure that might trace back to its first moments, to processes that occurred when space and time themselves were being born. These aren't just abstract ideas. They're attempts to understand real observations, real patterns in real data. They're scientists doing what scientists do, looking at the universe carefully, measuring it precisely, and trying to figure out what it's telling us. And what it might be telling us is that the cosmos has secrets, hidden symmetries, subtle structures, a character and history that's richer than we imagined. Or it might be telling us nothing. It might be that we're seeing patterns where none exist, fooled by statistical noise and cognitive biases. That's always possible in science. We won't know for certain until we have better data, more observations, deeper understanding. But either way, whether the cosmic axis is real or illusory, the process of investigating it is beautiful. It's humanity reaching out with instruments and mathematics, trying to comprehend the incomprehensibly large. It's us asking questions about the entire universe, questions that once would have seemed unanswerable, and finding that maybe, just maybe, we can start to answer them. That's worth celebrating. That's worth marveling at, even if you're half asleep. Drifting through these ideas, like drifting through a dream, you can appreciate the audacity of it, the ambition, the curiosity that drives us to wonder about such things. Let your mind wander now. Let these thoughts about spinning galaxies and cosmic axes float through your awareness without grasping at them. You don't need to understand every detail. You don't need to remember the names of researchers or the specific percentages of alignment. Just let the wonder of it wash over you. The universe is vast and ancient and mysterious, and somewhere in its vastness, there might be patterns we're only beginning to see. Alignments that hint at deeper truths. A hidden axis around which everything turns, slowly, quietly, patiently, over billions of years. We're going to keep exploring this mystery. There's more to discuss, other kinds of evidence, other theoretical frameworks, other ways of thinking about what it all means. But we have time. The night is long. The universe is patient. And we're in no hurry to reach any conclusions. Just breathe. Just rest. Just let the cosmos spin around you, real or imagined, while you settle deeper into the comfort of not knowing everything but being content to wonder. Now let's explore the structure of the universe on the larger scales. Let's talk about the cosmic web, that beautiful, intricate network of filaments, walls, and voids that fills all of space. When you look at maps of the universe created by large galaxy surveys, you see something remarkable. Galaxies aren't scattered randomly like stars on a dark canvas. They're organized into structures. Long, thin filaments of galaxies stretch across hundreds of millions of light years. Where filaments intersect, you find dense clusters containing thousands of galaxies. Between the filaments lie vast voids, enormous empty regions where few galaxies exist. The result looks like a web, or like foam, or like the scaffolding of some cosmic architecture built by processes we're still trying to fully understand. This structure formed over billions of years through the action of gravity. In the early universe, matter was distributed almost uniformly, with only tiny variations in density, the same variations we see in the CMB. But gravity amplifies density variations. Regions that were slightly denser attracted more matter, becoming denser still. Underdense regions lost matter to their denser neighbors, becoming emptier. Over time, this process created a hierarchical structure. Small overdensities merged to form larger ones. Galaxies formed in dense regions. Groups of galaxies merged into clusters. Clusters connected along filaments, forming superclusters, and the voids grew larger and emptier as matter flowed away toward the filaments and clusters. The cosmic web is the end result, or rather, the current snapshot, of this ongoing process. It's still evolving, still growing, still being shaped by gravity's patient hand. But here's what's interesting for our story. The cosmic web itself might have preferred orientations. The filaments might not point in random directions, but might be organized in ways that reflect some underlying structure in the universe. Several studies have looked at the orientations of cosmic filaments, the directions they point across space. This is challenging because defining a filament's orientation isn't straightforward. Filaments aren't rigid lines. They twist and curve. They branch and merge. They're more like tendons than like straight rods. But with sophisticated algorithms and large datasets, researchers can identify filaments and measure their approximate orientations. And when they do, they find hints, always hints, of large-scale alignments. One study from 2016 analyzed the cosmic web in a large volume of space surveyed by the Sloan Digital Sky Survey. The researchers identified thousands of filaments and measured their orientations in 3 dimensions. They found that filaments in certain regions showed correlations in their orientations. They tended to lie in similar planes or point in related directions. The effect was weak, only a few % deviation from randomness, but it was statistically significant and seemed to correlate with the large-scale structure of the universe in that region. It was as if the cosmic web had a grain, like wood, with filaments preferring to run along certain directions rather than others. Another study looked at the shapes of cosmic voids. Voids aren't perfectly spherical. They're often elongated, shaped like ellipsoids or cigars, and the directions of those elongations, the major axes of the voids, showed correlations across large distances. Why would voids have aligned shapes? One possibility is that voids grew along existing structures in the primordial universe. If there were large-scale flows or density gradients in the early cosmos, voids would expand preferentially in certain directions, creating elongated shapes that remember those initial conditions. Or perhaps the alignment of void shapes reflects the tidal gravitational fields in the cosmic web. Voids are surrounded by filaments, and the gravitational pull from those filaments might shape how voids expand, creating elongations that align with the filaments themselves. These are subtle effects, difficult to measure and interpret, but they add to the growing body of evidence suggesting that the universe's large-scale structure might not be as isotropic as we once assumed. There's also the matter of cosmic flows. Galaxies aren't just sitting still in space. They're moving, sometimes toward us, sometimes away, sometimes sideways. Some of this motion is due to the expansion of the universe, but there's also peculiar motion relative to the expansion, caused by gravitational attraction to nearby structures. When astronomers measure the velocities of many galaxies, they can map out these peculiar motions and infer the gravitational fields causing them. This reveals the distribution of matter, including dark matter, which is invisible but exerts gravitational pull. And what they find is fascinating. There are large-scale flows of galaxies, streams of motion spanning hundreds of millions of light-years. Our local group of galaxies is moving toward a massive concentration of matter called the Shapley supercluster. But the motion isn't just toward the Shapley supercluster. There seem to be even larger-scale flows, pulling on the Shapley supercluster itself. Some researchers have proposed that there are enormous structures beyond our observable horizon, structures whose gravity reaches into our patch of the universe and influences the motion of galaxies here. These hypothetical structures have been given names like the Great Attractor and the Dark Flow, though their existence remains controversial. If such structures exist, they would create preferred directions in the cosmic flow field. And those preferred directions might show up in other ways, in the alignments of galaxies, in the orientations of filaments, perhaps even in the patterns of the CMB. This is speculative, of course. The evidence for structures beyond our horizon is indirect and contested. But it's another way that the universe could have a hidden axis, a preferred direction imprinted by the gravitational influence of matter we can't directly observe. Let's think about the cosmic web from a different perspective. Let's think about its symmetry, or lack thereof. In mathematics, there's a concept called homogeneity and isotropy at different scales. The universe might be homogeneous and isotropic when you average over very large volumes, say 1 billion light-years on a side. But at smaller scales, it's clearly not homogeneous. There are galaxies here, voids there, filaments connecting them. The structure is lumpy, hierarchical, complex. The question is, what's the transition scale? At what size do you have to zoom out before the universe looks uniform? And is that transition scale the same in all directions? Or does the universe become homogeneous more quickly in some directions than others? If the universe has a preferred axis, you might expect the transition to homogeneity to be anisotropic. The universe might become uniform faster when you average along the axis than when you average perpendicular to it. This would be a signature of broken isotropy, a hint that space has a direction built into it. Some studies have tried to measure this. They look at how the distribution of galaxies becomes more uniform as you increase the scale of averaging. And they check whether this convergence to uniformity happens at the same rate in all directions. The results are inconclusive. Some studies find hints of anisotropy in the convergence. Others find the universe becomes uniform at roughly the same scale in all directions, within the uncertainties of the measurements. But the fact that we can even ask such questions, that we have enough data to test the isotropy of the universe at different scales, is remarkable. A century ago, we barely knew that galaxies existed. Now we're mapping the structure of the cosmos across billions of light-years and testing fundamental assumptions about its symmetry. Let's pause here and consider what the cosmic web tells us about the universe's history. Every filament, every cluster, every void is a fossil record of processes that occurred over billions of years. The structure we see today is the result of tiny fluctuations in the early universe, amplified by gravity into the magnificent architecture of the cosmic web. If the early universe had perfect isotropy, no preferred directions, no large-scale asymmetries, then the cosmic web should also be isotropic, at least statistically. Any individual filament might point in some random direction, but the overall distribution of orientations should be uniform. But if the early universe had anisotropies, if the CMB's axis of evil is real, if there were primordial flows or rotations or magnetic fields with preferred directions, then those anisotropies would be inherited by the cosmic web. The filaments would remember the orientations imprinted in the initial conditions. The voids would expand along directions determined by primordial gradients. The whole structure would carry an imprint of that earlier symmetry, faint but detectable if you look carefully enough. That's what makes these observations so important. They're not just measuring the current structure of the universe. They're looking back in time, reading the fossil record, trying to understand what the universe was like in its infancy. And if that infant universe had a preferred direction, we need to understand why. What process during the Big Bang, or during inflation, or in whatever came before, could have created such an asymmetry? What does it tell us about the fundamental nature of space and time? These are deep questions, questions that probe the boundaries of our knowledge, that push us to think about the universe in new ways. And they're questions we can actually investigate using telescopes and computers and the ever-growing mountain of data about the cosmos. Let's talk about simulations. One of the most powerful tools in modern cosmology is the computer simulation. Researchers create virtual universes, starting with initial conditions based on our understanding of the early cosmos, and let the laws of physics, gravity, fluid dynamics, radiation transport play out over billions of simulated years. These simulations produce virtual cosmic webs that can be compared to observations. If the simulated web looks like the real one, it suggests our understanding of the initial conditions and the physical processes is correct. If there are discrepancies, it tells us something is missing from our models. Simulations of the cosmic web generally match observations quite well. They reproduce the filamentary structure, the distribution of void sizes, the properties of galaxy clusters. This is a triumph of modern cosmology. We can create virtual universes that look remarkably like the real one. But most simulations start with isotropic initial conditions. They assume the early universe had no preferred directions, only random fluctuations in density. And yet they still produce cosmic webs that occasionally show local alignments of filaments or correlated void shapes, just from the randomness of how structures happen to form. So when we observe alignments in the real universe, we have to ask, are these alignments stronger than what simulations predict? Are they evidence of true anisotropy in the initial conditions, or just random chance that happens to produce noticeable patterns? This is where statistics becomes crucial. We need to quantify exactly how aligned filaments are, how correlated void shapes are, how strong galaxy spin alignments are. Then we need to compare those measurements to what simulations predict. If the observed alignments are significantly stronger than simulated ones, it suggests something's missing from our models, perhaps initial anisotropies that we haven't included. But if the observed alignments are consistent with simulations, it means the patterns we're seeing might just be coincidence. They might look meaningful to us because humans are pattern-seeking creatures, but they might not reflect any fundamental anisotropy in the universe. This comparison is ongoing. Different research groups are running ever larger simulations, using ever more sophisticated physics, and comparing them to ever better observational data. The answer isn't clear yet. The alignments might be significant, or they might be noise. We're still figuring it out. And that's okay. That's how science works. It's messy. It's uncertain. It's full of ambiguities and debates and contradictory findings. But slowly, as more data accumulates and more analyses are performed, the picture becomes clearer. Patterns that are real persist. Patterns that are illusions fade away. We're patient. We're willing to wait for the truth to emerge. Because understanding the structure of the universe, really understanding it, not just cataloguing galaxies but comprehending the deep patterns and processes that shaped everything, is worth the wait. Let your mind drift through the cosmic web now. Imagine yourself floating through one of those vast filaments, surrounded by galaxies like jewels strung along an invisible thread. Imagine the silence, the emptiness, the profound loneliness and beauty of intergalactic space. And imagine wondering, does this filament point in a special direction? Is it aligned with a cosmic axis, a hidden structure in space-time itself? Or is it just one random thread in a random tapestry, meaningful only because you happen to be there, observing it, asking questions about it? You might never know the answer, but the question itself is beautiful. The possibility itself is worth contemplating. Because even if the cosmic web is perfectly random, perfectly isotropic, the fact that we can ask about it, that we can measure it, that we can compare observations to simulations and test our theories against reality, that fact alone is extraordinary. We're part of the universe trying to understand itself. Conscious matter organized into complex patterns, looking outward at other patterns, seeking meaning, seeking order, seeking truth. And whether we find it or not, the search itself gives our lives a kind of cosmic significance. Rest now. Let the cosmic web cradle you, its filaments stretching across space like the most delicate lace, woven from galaxies and dark matter and the patient work of gravity over eons. Let yourself be part of it, connected to everything, floating gently through the vast structure of existence. We'll continue soon. There's more to explore, more evidence to examine, more theories to consider. But for now, just be, just drift. Just let the universe hold you in its incomprehensibly large embrace while your mind wanders through filaments and voids and the quiet spaces between stars. Now let's turn to theory. Let's explore the ideas that physicists and cosmologists have proposed to explain, or explain away, the hints of a cosmic axis. These are frameworks for understanding mathematical structures that might account for the observations we've been discussing. Some of these theories are conservative, requiring only small modifications to our current understanding. Others are radical, proposing entirely new physics or geometry. And some suggest that what we're seeing isn't evidence of a cosmic axis at all, but rather artifacts of how we observe and interpret the universe. Let's start with the simplest explanation: statistical fluctuations, pure chance, coincidence. In any finite dataset, there will be patterns. If you flip a coin 100 times, you'll occasionally get 5 heads in a row, even though each flip is random. If you analyze the temperature of the CMB across millions of pixels, some patterns will emerge just by luck, even if the underlying process is completely random. The question is, are the patterns we observe in the CMB and galaxy alignments more extreme than what you'd expect from chance? Statistical analysis tries to answer this by calculating p-values, the probability that a pattern as strong as the observed one could arise from pure randomness. For the axis of evil in the CMB, the p-value is typically around 1%. This means there's a 1% chance that the alignment of the quadrupole and octopole is just coincidence. That's suggestive, but not conclusive. In particle physics, discoveries usually require p-values of 0.0003% or better, the famous 5 sigma threshold. The CMB axis doesn't meet that standard, so it's possible, quite possible, that the axis is a statistical fluke. We happen to observe a universe where, by pure chance, the quadrupole and octopole aligned. If we could observe, so it's possible, quite possible, that the axis is a statistical fluke. We happen to observe a universe where, by pure chance, the quadrupole and octopole aligned. If we could observe 1,000 universes, this alignment might appear in 10 of them, and we just happen to live in one of the 10. This explanation is unsatisfying, but it's honest. And it's important to keep in mind. Science should be skeptical, especially of extraordinary claims. An axis running through the entire universe is an extraordinary claim, and it requires extraordinary evidence. But let's explore the alternatives. What if the axis is real? What physical mechanisms could create it? One possibility involves modifications to inflation. As we mentioned earlier, inflation is the idea that the very early universe underwent exponential expansion, growing from subatomic scales to cosmic scales in a fraction of a second. This expansion smoothed out the universe, erasing most irregularities and creating the uniformity we observe. Standard models of inflation use a single scalar field, the inflaton, to drive the expansion. This field is isotropic, meaning it has the same properties in all directions. When inflation ends, the universe inherits that isotropy, leading to a CMB with no preferred directions. But what if inflation involved more than one field? What if there were multiple fields with different properties, or a single field with directional characteristics? These are called anisotropic inflation models, and they can produce universes with preferred directions. Imagine the inflaton field as an arrow rather than a sphere. As space expands, the arrow's direction is preserved, stretched across cosmic scales. This direction would affect how quantum fluctuations during inflation became density fluctuations, creating patterns in the CMB that reflect the arrow's orientation. Anisotropic inflation models have been studied extensively. They can reproduce the observed axis if their parameters are tuned appropriately. But they also make other predictions about the detailed structure of CMB fluctuations, about gravitational waves, about the spectrum of density perturbations, and not all observations match those predictions. So, while anisotropic inflation is possible, it's not yet clear whether it's the right explanation. Another theoretical framework involves cosmic defects. These are hypothetical structures that could have formed during phase transitions in the early universe, similar to cracks that form when water freezes into ice. There are different types of defects: cosmic strings, one-dimensional; domain walls, two-dimensional; monopoles, point-like; and textures, a more complex topology. Each type has different properties and would affect the universe differently. A cosmic string, for instance, is an extraordinarily thin line of concentrated energy stretching across space. If a long string passed through the region where the CMB formed, it would create a characteristic pattern, a discontinuity in temperature across the sky, with specific correlations between the quadrupole and octopole. Some researchers have suggested that the axis of evil could be the signature of a cosmic string that passed through our observable universe. The string itself would have decayed long ago, but its imprint would remain in the CMB, a scar from the universe's traumatic youth. This is a fascinating idea, but it faces challenges. Cosmic strings should create other signatures too: patterns in the CMB at smaller scales, effects on the polarization of light, perhaps even gravitational wave signatures. Some of these have been looked for but not found, which constrains how strong any cosmic strings could be. Still, the possibility remains. The universe might have scars, might have defects, might have structural features imprinted during phase transitions we don't fully understand, and those features might be responsible for the anomalies we observe. Let's talk about topology again, but in more detail this time. The topology of space refers to its global shape, how it connects to itself, whether it's finite or infinite, whether it has boundaries or loops back on itself. Most cosmological models assume space is simply connected and infinite. But space could have a more exotic topology. It could be finite, wrapping around on itself like the surface of a sphere or a torus. Or it could be multiply connected, with different regions of space linked in non-intuitive ways. If space has unusual topology, light traveling through it would behave strangely. Photons could take multiple paths from the same source to the same observer, arriving at different times. Or the finite size of space could create a cutoff in the wavelengths of allowed fluctuations, suppressing large-scale structure in the CMB. Some topological models predict specific patterns in the CMB, patterns that include alignments of the quadrupole and octopole. This is because the finite geometry constrains how fluctuations can organize themselves, creating correlations that wouldn't exist in infinite space. Researchers have searched for other signatures of unusual topology. One signature would be matching circles in the CMB, regions where you see the same pattern repeated, because light from the same source has traveled around the universe via different paths. Despite careful searches, no convincing matching circles have been found. This doesn't rule out exotic topology, but it constrains it. If space loops back on itself, the loop must be larger than the observable universe, so the matching circles would be too faint or distorted to detect. Or the topology must be of a type that doesn't produce matching circles, perhaps a more complex manifold where light paths don't close in simple ways. The cold spot in the CMB has also been speculatively linked to topology. Some models suggest it could be a signature of a topological feature, a kind of wormhole or handle connecting distant regions of space. But these ideas are highly speculative and lack strong observational support. Another theoretical avenue involves modifications to general relativity. Einstein's theory has been tested extensively and works extraordinarily well, but it's possible that on the largest scales approaching the size of the observable universe, gravity behaves slightly differently than Einstein predicted. There are many modified gravity theories. Some add extra terms to Einstein's equations, others introduce new fields that couple to gravity. Still others change the fundamental structure of space-time itself, making it discrete rather than continuous, or adding extra dimensions that we don't directly perceive. Some modified gravity theories predict anisotropies. They allow for preferred directions in how gravity propagates or how space-time curves. If gravity works differently in different directions, you'd expect to see asymmetries in the universe's structure, in the CMB, in the motions of galaxies. Testing modified gravity is challenging because the predictions often differ only slightly from general relativity, and the differences appear most prominently at scales that are hard to observe. but cosmologists are working on it, designing tests that could distinguish between Einstein's theory and its competitors. If one of these modified theories turns out to be correct, it could explain the cosmic axis. The preferred direction might be a fundamental feature of how gravity works, woven into the structure of spacetime at the deepest level. Let's consider quantum mechanics. At the smallest scales, the universe is governed by quantum laws, probabilities, uncertainties, superpositions of states. And quantum mechanics is strange enough that it might have implications for cosmology. One idea is that the universe, at the moment of the Big Bang or during inflation, existed in a quantum superposition, many possible configurations overlaid on top of each other. When the universe decohered, when quantum superpositions collapsed into definite classical states, the particular configuration that emerged might have had preferred directions by chance. This doesn't explain why the direction would align with our solar system, but it could explain why the universe has an axis at all. The universe might have chosen a particular orientation from among many quantum possibilities, and that choice is now visible in the CMB and other observations. Another quantum idea involves entanglement. In quantum mechanics, particles can be entangled, meaning their properties are correlated even across vast distances. Some physicists have speculated that regions of the early universe might have been quantum entangled in ways that created long-range correlations in the density field. If those entangled regions happen to have a net angular momentum or a preferred direction, that preference would be preserved as the universe expanded. The result would be a cosmic axis, a remnant of quantum correlations from the universe's earliest moments. These quantum cosmology ideas are deeply speculative. We don't have a complete theory of quantum gravity, a framework that unifies quantum mechanics and general relativity, so any discussion of the quantum state of the universe is partly guesswork. But they're intriguing possibilities, ways that the weirdness of quantum mechanics might reach up to cosmic scales and shape the structure of everything. Now let's talk about something called the cosmological principle, because it's central to this whole discussion. The cosmological principle is the assumption that the universe, on large scales, is homogeneous and isotropic. It looks the same everywhere and in every direction. This principle isn't derived from deeper laws. It's an assumption, a simplifying choice that makes cosmology tractable. With the cosmological principle, Einstein's equations become much simpler, reducing to a manageable set of differential equations that describe how the universe expands and evolves. Without the cosmological principle, cosmology becomes far more complicated. You have to account for variations in density, in expansion rate, in the curvature of space from place to place. The mathematics becomes forbidding, but just because the cosmological principle is convenient doesn't mean it's true. It might be an approximation, valid to a certain degree, but breaking down when you look carefully enough. And the hints of a cosmic axis, if real, would be evidence that the principle is approximate rather than exact. This wouldn't overturn cosmology. The universe can still be approximately homogeneous and isotropic on large scales, even if there are subtle asymmetries. Most predictions of the standard cosmological model would still hold. But we'd need to refine our models, adding terms that account for the anisotropies, and we'd need to understand what caused those anisotropies in the first place. Some cosmologists have proposed models where the universe is homogeneous but not isotropic, the same everywhere, but with a preferred direction. These are called Bianchi models, after the Italian mathematician who first classified them. In Bianchi universes, space expands at different rates in different directions, creating a cosmic shear or rotation. Bianchi models can produce anisotropies in the CMB similar to what's observed, but they also predict other effects, systematic patterns in galaxy velocities, distortions in the Hubble expansion, that haven't been clearly detected. So while Bianchi models are possibilities, they're not yet compelling explanations for the data. Let's talk about observational systematics. This is a less exciting explanation, but an important one. Observational systematics are errors or biases in how we collect and analyze data. They can create false patterns, artifacts that look like real signals, but are actually glitches in our instruments or mistakes in our analysis. The CMB satellites, COBE, WMAP, Planck, are marvels of engineering. They're exquisitely sensitive instruments operating in the harsh environment of space. But they're not perfect. They have instrumental noise. They have beam patterns, the way their antennas pick up light from different directions, that must be carefully calibrated. They're affected by radiation from our solar system, by interference from Earth's atmosphere, by cosmic rays zipping through space. All of these effects are accounted for in the data analysis, but the accounting isn't perfect. There might be subtle systematics that haven't been fully removed, and those systematics might create false patterns that mimic a cosmic axis. The teams that operate these satellites have spent enormous effort looking for systematics. They've tested their instruments exhaustively. They've developed sophisticated pipelines for processing the data, removing foregrounds, correcting for instrumental effects. And they've released their data publicly, allowing independent researchers to check their work. Despite all this scrutiny, some level of systematic error is always possible. And until we have completely independent measurements of the CMB, perhaps from a new satellite using different technology, or from ground-based observations at different frequencies, we can't be absolutely certain that the axis is real rather than instrumental. The same applies to galaxy alignments. Measuring the spin of a galaxy from a two-dimensional image is tricky. You have to account for the galaxy's orientation, for dust that might obscure parts of it, for whether you're seeing spiral arms or some other feature. Different algorithms can give different results, and if there's a bias in how the algorithms work, it could create false correlations. This is why reproducibility is so important in science. Multiple independent teams using different data and different methods need to find the same result before we trust it. And for the cosmic axis, we're not quite there yet. Some studies find it, others don't, and the debates continue. So we're left in an uncertain place. The axis might be real, a genuine feature of the universe that tells us something profound about its structure and history. Or it might be a combination of statistical fluctuations and subtle systematic errors, a mirage that will fade as our instruments and methods improve. Both possibilities are worth taking seriously. Science progresses by holding multiple hypotheses in mind, testing them against observations, and gradually narrowing down what's true. We're in the middle of that process now, and the outcome isn't yet clear. Let your mind rest for a moment. We've covered a lot of theoretical ground, from inflation to topology, from quantum mechanics to observational systematics. These ideas connect and overlap in complex ways, forming a web of possibilities as intricate as the cosmic web itself. The universe might have an axis, or it might not. And either way, the process of figuring it out is beautiful. It's science at its best. Careful observation, rigorous analysis, creative theorizing, and honest uncertainty about what it all means. We're not done yet. There's more to explore, more questions to ask, more ways of thinking about this mystery. But we're taking our time, letting each idea settle into place before moving to the next. Because the universe is patient, and so are we. Just breathe. Just drift. Just let these theories and possibilities float through your awareness, like clouds across a vast sky, each one interesting, each one provisional, each one part of humanity's ongoing attempt to understand the cosmos we inhabit. Let's drift now into stranger territory. Let's talk about the multiverse, the idea that our universe might be just one among many, perhaps infinitely many, each with different properties, different laws, different structures. The multiverse isn't science fiction. It's a serious idea that emerges from several independent lines of theoretical reasoning, and it has implications for how we think about the cosmic axis and other apparent anomalies in our universe. One version of the multiverse comes from eternal inflation. In this picture, inflation, the exponential expansion of the early universe, never completely stops. Instead, It ends in some regions of space, but continues in others. Where it ends, a pocket universe forms, like a bubble, nucleating in boiling water. That bubble is a universe like ours, with galaxies and stars and planets. But inflation continues elsewhere, creating more bubbles, more universes. And this process never ends. It's eternal, producing an infinite number of pocket universes, each one causally disconnected from the others, each one potentially having different physical properties. In this framework, our universe is just one bubble among infinitely many. And the properties we observe, the strength of forces, the masses of particles, the structure of spacetime, might be different in other bubbles. They might vary randomly from universe to universe, determined by chance during the formation of each bubble. If the multiverse exists, it has profound implications for how we interpret observations. Consider the cosmic axis. If it's real, we need to explain why our universe has it. But if infinitely many universes exist, some fraction of them will have axes just by chance. There'll be statistical outliers, universes where the quadrupole and octupole happen to align, or where some initial anisotropy got preserved through inflation. We might simply live in one of those universes, not because there's any deep physical reason for the axis to exist, but because the multiverse contains every possibility, including universes with axes. We observe an axis because we happen to inhabit a universe that has one, just as we observe 3 spatial dimensions and particular values for fundamental constants. This is called anthropic reasoning. It's the idea that some features of our universe might not have deep explanations, but are simply prerequisites for observers to exist. We couldn't observe a universe without certain properties, because those properties are necessary for life, or at least for complexity, or at least for something like conscious observers to emerge. For example, if the strength of gravity were much different, stars might not form, or they might burn out too quickly for planets to develop. If the electromagnetic force were much stronger or weaker, atoms might not be stable, or chemistry might be too simple to produce life. The fact that we observe forces with the particular strengths they have might be because those strengths are necessary, or at least conducive, to our existence. Could the cosmic axis have an anthropic explanation? It's hard to see how. The axis doesn't seem to be necessary for life or consciousness. Galaxies would still form, stars would still shine, planets would still orbit, whether or not the CMB has a quadrupole-octupole alignment. So if the axis is real, anthropic reasoning doesn't explain it. But the multiverse idea still provides context. It reminds us that not every feature of our universe needs a fundamental explanation. Some features might be accidents, quirks, random choices made during the universe's formation that could have gone differently. Another version of the multiverse comes from quantum mechanics. In the many worlds interpretation, one of several ways of understanding quantum theory, every quantum measurement creates a branching of reality. Each possible outcome occurs in a different branch, a different version of the universe. Over time, this branching produces an unfathomably large number of parallel universes, all evolving simultaneously but unable to interact with each other. In some branches, you're reading this script. In others, you're doing something else. In still others, you never existed at all because some quantum event in the past went differently. In this quantum multiverse, every possible history occurs in some branch, and that includes histories where the CMB has an axis, and histories where it doesn't. Histories where galaxies align in particular ways, and histories where they don't. From our perspective, we observe one particular branch, the one we happen to inhabit. And that branch might have a cosmic axis, simply because across all branches, every configuration eventually appears. We're not special. We're just one outcome among infinitely many. This is philosophically unsettling for many people. It seems to drain meaning from observations, reducing everything to, it is what it is, because that's the branch we're in. And it doesn't help explain why we're in this particular branch rather than another. But it does suggest that we should be cautious about demanding deep explanations for every observed feature. Some features might be accidents of quantum history, with no more significance than the particular pattern of raindrops on a window. Let's consider another angle: the fine-tuning problem. Our universe seems remarkably fine-tuned for complexity. The fundamental constants, the strength of forces, the masses of particles, the rate of cosmic expansion, all have values that fall within narrow ranges that allow for interesting structures like galaxies, stars, and life. If these constants were significantly different, the universe would be radically altered. It might expand too quickly for matter to clump together, or collapse back on itself before stars could form, or be filled with nothing but black holes, or be so smooth and featureless that nothing interesting ever happened. The fine-tuning of these constants is a puzzle. Is it coincidence, design, or is it explained by the multiverse? If infinitely many universes exist with different constants, we necessarily find ourselves in one of the rare universes where the constants allow for complexity. The cosmic axis, if real, doesn't fit neatly into the fine-tuning discussion. It's not a constant that could be tuned. It's a feature of the universe's structure, possibly a consequence of initial conditions or symmetry breaking. But it does raise similar questions about why we observe what we do. If the multiverse exists and different universes have different initial conditions, some will have axes and some won't. We observe an axis, assuming it's real, simply because we're in one of the universes that has one. There's no deeper reason, no fundamental law that requires it. It's just how our particular universe happened to start out. This is intellectually honest, but somewhat dissatisfying. It turns cosmology from a search for fundamental explanations into a kind of cosmic anthropology, cataloguing the properties of our particular universe without being able to say why it has those properties rather than others. Some physicists find this troubling. Others embrace it, arguing that expecting every feature of our universe to have a deep explanation is anthropocentric. It assumes the universe exists to make sense to us, which is a kind of cosmic narcissism. Let's talk about testability. One criticism of multiverse theories is that they're not testable. If other universes are causally disconnected from ours, if no information can flow between them, then we can never observe them directly. We can't confirm or refute the multiverse hypothesis with measurements. This makes some scientists uncomfortable. They argue that untestable ideas aren't science, that the multiverse is metaphysics or philosophy rather than physics. And there's some validity to this concern. Science works by making predictions that can be tested against observations. If a theory doesn't make testable predictions, it's not clear how to evaluate it scientifically. But defenders of the multiverse argue that it does make indirect predictions. For instance, eternal inflation predicts certain patterns in the CMB and certain statistical properties of the observable universe. We can test those predictions, and if they're confirmed, it lends support to the eternal inflation framework, which in turn implies a multiverse. Similarly, if we develop a complete theory of quantum gravity, it might naturally imply many universes or one universe. We can't directly observe other universes, but we can test the underlying theory that predicts them. And some physicists argue that even if we can't observe other universes, the mere logical consequence of our best theories is evidence enough. If the mathematics of inflation or quantum mechanics naturally produces multiple universes, and those theories work extraordinarily well in every other domain, then we should take the multiverse seriously even if we can't see it. This is an ongoing philosophical debate within physics, with reasonable people on both sides. For our purposes, it's enough to note that the multiverse is a possibility, one that affects how we interpret observations like the cosmic axis. If the multiverse exists, the axis might be a random feature with no deep explanation. If the multiverse doesn't exist, we need to explain why our single universe has this particular property. Either way, the question is interesting, and the answer matters for how we think about the cosmos. Let's consider one more idea: the simulation hypothesis. This is the notion that our universe might be a simulation running on some vastly powerful computer in a higher reality. It sounds like science fiction, but it's been discussed seriously by philosophers and physicists. The argument goes something like this. If it's possible to create detailed simulations of universes, and if advanced civilizations eventually develop the technology to do so, then there might be many simulated universes and only one real base universe. By sheer numbers, any given observer is more likely to be in a simulation than in the base reality. If we're in a simulation, some features of our universe might be artifacts of how the simulation is constructed. Perhaps the cosmic axis is a remnant of how the simulation was initialized, or a consequence of the discrete grid on which the simulation runs, or some other computational artifact. This is highly speculative, of course. We have no evidence that we're in a simulation, and the idea raises more questions than it answers. But it's another framework for thinking about anomalies in the cosmos. They might not be features of physical reality, but features of the computational substrate underlying reality. Most physicists don't take the simulation hypothesis very seriously as a practical explanation for observations. But it's interesting as a thought experiment, a reminder that our understanding of reality might be incomplete in ways we haven't even imagined. All of these ideas, the multiverse, anthropic reasoning, quantum branching, simulations, share a common theme. They suggest that the universe might be more complex, more layered, more subtle than we typically assume. Our observations might be just one slice of a much vaster reality, and what we see might not represent fundamental truth, but rather contingent facts about our particular corner of existence. This can feel unsettling. We want the universe to make sense. We want our observations to reveal deep truths, not just random accidents. We want to understand why things are the way they are, not just catalogue what they happen to be. But maybe that desire for deep explanations is itself a bias, a human tendency to see meaning and purpose where none exists. Maybe the universe is just what it is, and some of its features, like the cosmic axis, if it's real, are quirks of history with no profound significance. Or maybe there are deep explanations, and we just haven't found them yet. Maybe the axis and the alignments of galaxies and all the other hints of anisotropy are telling us something important about the universe's fundamental structure. Maybe they're clues that will lead us to new physics, new understanding, new ways of seeing reality. We don't know yet. And that's okay. That uncertainty is part of the adventure, part of what makes science exciting. We're exploring the boundaries of knowledge, peering into the unknown, and we're finding that the unknown is larger and stranger than we imagined. Let these ideas wash over you now. The multiverse, parallel realities, quantum branches, cosmic accidents, deep truths waiting to be discovered. Or no deep truths at all, just endless complexity with no underlying meaning. It's a lot to contemplate. And you don't need to reach any conclusions. You don't need to decide what you believe or what makes sense. Just let the possibilities exist in your mind, floating peacefully like stars scattered across the night sky, each one a point of light that might be something profound or might be nothing special at all. We're nearing the end of our journey through this cosmic mystery. There are a few more things to discuss, a few more perspectives to consider, but we're taking our time, letting each idea have its moment, letting the full picture slowly assemble itself in the quiet spaces of your awareness. Just breathe, just rest, just drift along with these thoughts, wherever they take you, knowing that the universe, however it's structured, however many axes or symmetries or quirks it has, is vast enough to contain all our questions and patient enough to wait for answers. Let's bring this journey toward a gentler place now. Let's talk about what the cosmic axis, real or illusory, means for us as human beings, living our small lives on a small planet in a vast universe. At first glance, it might seem to mean nothing. Whether the universe has a preferred direction or not doesn't affect your daily life. The sun still rises. Gravity still pulls you toward Earth. Water still flows downhill. The presence or absence of a cosmic axis 10 billion light-years away has no impact on your breakfast, your job, your relationships, your hopes and fears. And that's true, in a practical sense. Cosmology doesn't change everyday life. Knowing about the CMB's quadrupole-octopole alignment won't help you pay your bills or improve your health or make your loved ones happier. But in a deeper sense, cosmology does matter. Because we are the universe becoming conscious of itself. We are matter that has organized itself into patterns complex enough to think, to wonder, to ask questions about where it all came from and where it's all going. When we look at the night sky and wonder if the stars are aligned around some hidden axis, we're exercising one of humanity's most distinctive capacities, the ability to contemplate scales far beyond ourselves. We can think about billions of light years and billions of years. We can use mathematics and instruments to probe realities that our senses can't directly perceive. We can discover truths about the cosmos that no amount of casual observation would ever reveal. That's extraordinary. That's worth celebrating, even if the truths we discover are uncertain or incomplete. The cosmic axis, if it exists, is a reminder that the universe might be more interesting than the simplest models suggest. It's a reminder that assumptions should be tested, that what seems obvious might be wrong, that nature is under no obligation to conform to human expectations. For thousands of years, people assumed the Earth was the center of the universe. Then Copernicus and Galileo showed that Earth orbits the Sun. Later, astronomers discovered that the Sun is just one star among billions in the Milky Way. And then, they found that the Milky Way is just one galaxy among billions in the observable universe. Each of these discoveries was a kind of demotion. We are not central. We are not special. We are just one tiny part of an incomprehensibly vast cosmos, with no privileged position or unique importance. The cosmological principle, the assumption that the universe is isotropic, is an extension of this idea. It says the universe has no center, no edge, no preferred direction. Every location and every orientation is equally valid. We see what we see, not because we're special, but because we happen to be here, and here is the same as anywhere else. But the cosmic axis, if real, would be a small step back from that complete democracy of location and direction. It would say the universe does have a preferred direction, at least in some subtle sense. That direction wouldn't be Earth's axis or the Milky Way's axis. It wouldn't put us back at the center of anything. But it would mean the universe has more structure, more character, more history written into its geometry than we thought. And that's a kind of poetry. The universe isn't just a blank expanse of space filled with randomly distributed galaxies. It's a structured entity, shaped by its origin, carrying memories of its youth, organized in ways we're only beginning to perceive. When you look up at the stars tonight, if you have a chance to see them, if light pollution and clouds don't obscure them, you might think about this. You might wonder if those stars and the galaxies beyond them are all part of a grand pattern. If they're all spinning in a coordinated way around an axis so large it stretches from one edge of the universe to the other. You probably won't be able to see the axis. It's not visible to the naked eye. It's only apparent in the statistics of galaxy orientations, in the patterns of ancient light, in the subtle alignments that require telescopes and computers to detect. But it might be there, and if it is, you're part of it. You're rotating with Earth, which orbits the Sun, which orbits the galactic center, which moves through intergalactic space, possibly influenced by this grand cosmic alignment that connects everything. That's a beautiful thought. Not in a mystical sense. We're not talking about fate or destiny or spiritual significance. But beautiful in the sense that everything is connected, not through magic, but through the patient work of gravity and the geometric structure of space-time. Every atom in your body was forged in the core of a star or in the explosion of a supernova. You are made of stardust, as Carl Sagan famously said, and those atoms have been on a journey for billions of years, through the interstellar medium, through the formation of the solar system, through the complex chemistry of life on Earth, to end up as part of you. And during that whole journey, those atoms have been part of the cosmic web, part of the grand structure of the universe, possibly aligned in some subtle way with the hidden axis we've been discussing all night. You are not separate from the cosmos. You are an integral part of it. And understanding the cosmos, even a little, even uncertainly, is a way of understanding yourself, your place, your connection to everything that exists. This is why people study cosmology. Not because it has practical applications, though sometimes it does. Not because it will make them rich or famous, though occasionally it does that too. But because it satisfies something deep in the human spirit, the desire to know, to understand, to see the world clearly and truthfully. The cosmic axis, whether it's real or not, is part of that quest. It's a question about the nature of reality, and asking that question makes us more fully human. Let's think about scale for a moment. It's easy to get lost in the enormity of cosmological distances and times. 1 billion light years is so vast that it's almost meaningless. Our brains didn't evolve to comprehend such scales. We can work with them mathematically, but we can't really feel them. But you can scale things down. You can think about the universe as a cosmic ocean, and yourself as a single drop of water in that ocean. The drop is tiny, seemingly insignificant, but it's made of the same substance as the ocean. It follows the same physical laws, and it's connected to every other drop through the fluid medium they all share. Or you can think of the universe as a vast tapestry, woven from threads of matter and energy. You're one thread in that tapestry, very small but essential. Remove your thread, and the tapestry would be different, even if only infinitesimally. You contribute to the pattern, even if you can't see the whole design. These metaphors are imperfect, of course, but they point toward a truth. You are part of something immeasurably larger than yourself, and that larger thing is not separate from you. It includes you. It is you, in a sense, just as the ocean is its drops, and the tapestry is its threads. The cosmic axis, if it exists, is a feature of that larger tapestry. And you're connected to it, not directly. It's not pulling on you, not exerting any force, but conceptually, structurally, as part of the same whole. This can be comforting. In moments when you feel small and alone and insignificant, it's worth remembering that you're part of a universe that's been evolving for nearly 14 billion years, that contains trillions of galaxies, that operates according to elegant mathematical laws, and that possibly has structure and beauty we're only beginning to discover. You're not just a random accident. You're an outcome of cosmic processes, a temporary organization of matter and energy that has the extraordinary property of being conscious. You're the universe experiencing itself, if only for a brief moment. And the questions you ask about the universe, even silly questions, even questions you ask half asleep in the middle of the night, are the universe asking questions about itself. That's what makes them meaningful. Let's talk about mystery. One of the remarkable things about science is that it doesn't eliminate mystery. It transforms mystery into different forms, often deeper and more interesting ones. 1,000 years ago, people looked at the night sky and saw mystery. They didn't know what stars were, or how far away they were, or why they moved across the sky. They invented myths to explain it, gods and heroes, cosmic battles, celestial spheres. Today, we know what stars are. We understand nuclear fusion, stellar evolution, the life cycles of stars from birth in nebulae to death as white dwarfs or supernovae. We can measure distances to stars, calculate their masses and temperatures, predict their futures. But knowing all this doesn't make stars less mysterious. It makes them differently mysterious. We now wonder about how the first stars formed after the Big Bang, about whether other stars have planets with life, about the nature of the dark matter that outweighs stars 10 to 1, about whether the patterns we see in stellar distributions reveal some deeper structure in space itself. Science doesn't kill wonder. It deepens it. Every answer opens up new questions, more subtle and profound than the ones we started with. The cosmic axis is like that. Even if we confirm it exists, even if we figure out exactly what causes it, we'll still have mysteries. We'll wonder why the universe chose that particular mechanism, what it implies about the laws of physics, what other features of space-time we haven't discovered yet. And if we eventually determine that the axis is illusory, that it's just statistical noise or instrumental artifacts, that will be valuable too. We'll have learned something about the limits of our methods, about the importance of skepticism, about how easy it is to see patterns that aren't really there. Either way, the mystery continues. And that's good. A universe without mysteries would be a sad place, a place where there was nothing left to discover, nothing to wonder about. We'd be like children who have opened all their presents and found nothing surprising inside. The cosmos is generous with its mysteries. It offers us an endless supply of questions, each one leading to others, like a vast tree of knowledge that branches forever. We'll never reach the end of it. There will always be more to learn, more to discover, more to wonder about. And that's deeply comforting in its own way. It means the adventure never ends. No matter how much we learn, there's always further to go, always deeper to look, always new perspectives to consider. Let your mind rest now in that comfort. Let yourself feel connected to the universe, to its mysteries, to its vastness. You don't need to understand everything. You don't even need to understand a fraction of it. You just need to be part of it, which you already are, simply by existing. The cosmic axis might be real. It might not. But regardless, you're here, now, thinking about it. You're participating in the universe's slow process of understanding itself. You're adding your small thread to the vast tapestry of consciousness that has emerged from matter over billions of years. And that's enough. That's more than enough. That's everything. We're nearing the end of our gentle journey through cosmic mysteries. And it's worth pausing here to reflect on something that threads through everything we've discussed: uncertainty. Science is often portrayed as providing certainty, definitive answers, absolute truths. But that's not really how it works. Science is a process of progressively reducing uncertainty, of narrowing down the range of what might be true, of building models that match observations better and better over time. But it never reaches perfect certainty. There are always error bars, always statistical uncertainties, always alternative explanations that haven't been completely ruled out. And that's not a weakness of science, it's a feature. It's what keeps science honest, what prevents it from calcifying into dogma. The cosmic axis embodies this uncertainty. After decades of observations and analysis, we still don't know if it's real. We have evidence that suggests it might be. We have other evidence that suggests it might not be. We have theories that could explain it if it exists. We have reasons to be skeptical even if the measurements are accurate. We're suspended in a state of not knowing. And that state, while sometimes frustrating, is also beautiful. Think about certainty for a moment. Certainty is comfortable. When you're certain about something, you can stop thinking about it, stop questioning it, and move on to other concerns. Certainty provides closure, but certainty also closes off possibilities. Once you're certain, you stop looking for alternatives. You stop being curious about whether things might be different. You've decided what's true, and that decision shapes how you see everything else. Uncertainty keeps you open. It keeps you curious. It keeps you humble, aware that what you think you know might turn out to be wrong or incomplete. It makes you pay attention, because something unexpected might appear at any moment. The scientists studying the cosmic axis are living in this state of uncertainty. They don't know if the patterns they're seeing are real or artifactual. They don't know if the alignments mean anything or are just coincidence. And that uncertainty drives their work forward. It motivates them to collect more data, develop better analysis methods, test alternative hypotheses. If they were certain, if the axis were obviously real or obviously false, they could stop. But the uncertainty keeps them going, keeps them searching, keeps them refining their understanding. And there's something poetic about that. The universe isn't giving up its secrets easily. It's making us work for them. It's teaching us patience, rigor, carefulness. It's reminding us that truth is subtle and that discovering it requires more than just clever ideas. It requires meticulous observation and honest self-critique. This applies to life in general, not just cosmology. So much of life is uncertain. We don't know what the future holds. We don't know if our choices will work out. We don't know how other people truly feel, or what they're thinking, or whether we're understanding them correctly. And yet we live. We make decisions. We form relationships. We pursue goals. We do all this despite, or perhaps because of, the fundamental uncertainty that permeates existence. Learning to be comfortable with uncertainty is one of the great skills of life. It's the ability to act without knowing for sure, to commit without complete information, to trust even when trust might be misplaced. It's the ability to hold questions without demanding immediate answers. The cosmic axis is just one question among countless others. And whether we ever get a definitive answer to it or not, the act of asking the question, of investigating it carefully, of thinking deeply about what it might mean, that act itself is valuable. It's valuable because it exercises our capacity for wonder. It reminds us that the universe is larger and stranger than our everyday experience suggests. It connects us to something beyond ourselves, beyond our immediate concerns, beyond the narrow slice of reality we can directly perceive. And it's valuable because it models good thinking. Scientific thinking. The kind of thinking that starts with observations, formulates hypotheses, tests them against evidence, and updates beliefs based on what the data shows rather than what we want to be true. This kind of thinking is rare. It doesn't come naturally. Our brains evolved to make quick judgments, to see patterns even when they're not there, to confirm what we already believe, rather than challenge it. Science is a set of tools and practices that help us overcome these biases, to think more clearly and see more accurately. The uncertainty around the cosmic axis is science working as it should. It's scientists being appropriately skeptical, demanding high standards of evidence, not rushing to conclusions. It's the scientific community checking and rechecking results, looking for flaws, proposing alternatives. This might seem slow or frustrating to outsiders. Why can't they just decide whether the axis is real or not? Why do they keep hedging, qualifying, saying maybe and possibly, and the data suggests but doesn't prove? But this caution is necessary. Science has been wrong before. Researchers have announced discoveries that turned out to be errors or artifacts. The history of science is littered with false positives, with patterns that seemed significant, but weren't, with theories that worked for a while, but eventually failed when better data came in. So scientists are careful, especially in cosmology, where observations are difficult and expensive, where you can't do controlled experiments, where you have only one universe to study. The standards of evidence are high, and that's appropriate. The cosmic axis might take decades to fully resolve. We might need new satellites, new telescopes, new surveys covering larger volumes of space. We might need theoretical breakthroughs that suggest new ways to test the hypothesis. We might need patient accumulation of data until the statistical uncertainties shrink to the point where we can be confident one way or the other. Or we might never know for certain. That's possible too. Some questions in cosmology might be fundamentally unanswerable, at least with the tools and methods available to us. The universe might be too vast, too old, too complex for us to fully comprehend from our tiny vantage point. And that's okay. That's part of the beauty. We're limited beings trying to understand unlimited reality. The fact that we can understand anything at all is miraculous. The fact that we can ask questions that probe the entire universe, that we can make measurements across billions of light years, that we can test our theories against observations, and refine them over time. All of this is extraordinary. Whether or not we ever definitively answer the question of the cosmic axis, the journey of asking it has already been worthwhile. We've learned things along the way. We've developed new techniques, new instruments, new ways of analyzing data. We've thought deeply about isotropy and symmetry and what they mean for cosmology. We've refined our understanding of the CMB, of galaxy formation, of the large-scale structure of space, and we've exercised our sense of wonder. We've reminded ourselves that the universe might always have surprises waiting for us, patterns we haven't noticed yet, structures we haven't imagined. We've stayed curious, stayed humble, stayed open to the possibility that what we think we know might be incomplete. Let yourself feel that openness now, that sense of possibility. The universe stretching out in all directions, full of things we understand and things we don't, things we've measured and things we've only glimpsed, certainties and uncertainties woven together into the fabric of reality. You don't need answers. You don't need closure. You can rest in the questions themselves, in the gentle space of not knowing, where curiosity lives and wonder thrives. The cosmic axis might exist, or it might not. And either way, you're part of a universe that's vast enough to contain both possibilities, complex enough to keep surprising us, and beautiful enough to make the search for understanding worthwhile. Just breathe. Just be. Just let the uncertainty wash over you like a gentle wave, carrying away the need for definitive answers and leaving behind only the peaceful awareness that some questions are worth asking, even if we never fully answer them. Before we close this gentle journey, let's look ahead. Let's talk about what comes next in the search for the cosmic axis, about the tools and missions that might finally resolve this mystery one way or another. Science doesn't stand still. Even as we speak, new instruments are being designed, new satellites are being built, new surveys are being planned. Each one pushes our capabilities a little further, lets us see a little deeper, measure a little more precisely. For the cosmic microwave background, the next generation of experiments is already underway. Ground-based telescopes in Antarctica and Chile are observing the CMB with incredible sensitivity, focusing particularly on its polarization, the orientation of the light waves, which carries information that temperature measurements alone can't reveal. The CMB is polarized because light scattering off free electrons during the epoch of recombination picks up a preferred orientation. This polarization has patterns that depend on the geometry of spacetime and the presence of gravitational waves from the very early universe. By measuring polarization carefully, scientists can test their models of inflation and probe conditions in the first fraction of a second after the Big Bang. If the cosmic axis is real and reflects some fundamental anisotropy in the early universe, it should show up in the polarization data in specific ways. Different theories make different predictions about how the axis would affect polarization patterns. So future polarization measurements will be crucial for determining whether the axis is real, and if so, what's causing it. There are also plans for new space missions. While nothing is currently scheduled to match the ambition of Planck, several concepts have been proposed for satellites that would measure the CMB with even greater precision, particularly in polarization. These missions are expensive and take years to develop, but they represent the future of CMB cosmology. Meanwhile, galaxy surveys continue to expand. The Sloan Digital Sky Survey, which has already provided so much data about galaxy distributions and properties, has been succeeded by even larger surveys. The Dark Energy Survey, the Kilodegree Survey, and other projects are mapping millions of galaxies across large fractions of the sky. And coming soon is the Legacy Survey of Space and Time, or LSST, which will be conducted by the Vera C. Rubin Observatory in Chile. Over 10 years, this survey will photograph the entire visible sky every few nights, creating an unprecedented dataset of billions of galaxies, their positions, their shapes, their colors. With data like this, measurements of galaxy alignments and cosmic web structure will become far more robust. If there are large-scale patterns in how galaxies spin or how filaments orient, LSST will find them. And if the patterns seen in smaller surveys turn out to be statistical flukes, LSST will reveal that too. There's also the Euclid mission, a European space telescope launched in 2023 that's now surveying billions of galaxies. Euclid is designed to study dark energy and dark matter, but its observations will also shed light on the large-scale structure of the universe and any potential anisotropies. Radio astronomy is advancing too. New radio telescopes and arrays are being built that will map the sky at radio wavelengths with unprecedented sensitivity. This will allow better studies of quasar polarization, of magnetic fields in intergalactic space, of the orientations of radio jets from active galaxies. One particularly exciting development is the Square Kilometre Array, or SKA, a massive radio telescope being built in Australia and South Africa. When complete, it will be the most sensitive radio telescope ever constructed, capable of detecting faint signals from the early universe and mapping cosmic structure in exquisite detail. The SKA and similar instruments will let us probe the cosmic web directly, tracing the filaments of hydrogen gas that connect galaxies and measuring how those filaments are oriented. If the cosmic web has large-scale alignments, radio observations will be one of the best ways to detect them. And then there are gravitational waves. We're now in the era of gravitational wave astronomy, with detectors like LIGO and Virgo regularly observing ripples in spacetime caused by colliding black holes and neutron stars. These observations open an entirely new window on the universe. Gravitational waves carry information about the objects that produce them, their masses, their spins, their orbits. But they also carry information about the spacetime through which they travel. If spacetime has anisotropies, if space is curved differently in different directions, gravitational waves would be affected in subtle ways. Future gravitational wave detectors, both on the ground and potentially in space, will be sensitive enough to test for these effects. They could detect whether spacetime has a preferred direction, whether the universe has a small rotation, whether there are large-scale distortions in the fabric of reality itself. All of these future observations will converge on the same question: is the universe truly isotropic, or does it have preferred directions? And if it has preferred directions, what do they tell us about the universe's origin and structure? The answer might come quickly, within the next decade or two, if the patterns are strong and consistent across different types of observations. Or it might take longer, requiring accumulation of ever larger datasets and ever more sophisticated analysis techniques. But eventually we'll know. We'll either confirm that the cosmic axis is real, or we'll determine with high confidence that it's not. And either answer will be interesting, will teach us something important about the cosmos. If the axis is real, it will reshape cosmology. It will tell us that our standard models need refinement, that the early universe was more complex than we thought, that spacetime itself might have structure we haven't accounted for. It will open up new lines of research, new theories to test, new mysteries to explore. If the axis is illusory, that will be valuable too. It will tell us about the limits of our methods, about how careful we need to be in interpreting data, about the importance of demanding high standards of evidence. It will remind us that nature is subtle, and that our intuitions about what patterns should exist can lead us astray. Either way, the search continues, because that's what science does. It asks questions, seeks answers, and asks deeper questions based on what it finds. It's an endless process, a journey without a final destination, a conversation with the universe that never truly ends. And you're part of that journey. Not directly, you're probably not analyzing CMB data or measuring galaxy spins, but conceptually, spiritually, as a conscious being who cares about these questions. Every time you wonder about the universe, every time you're curious about how things work or why things are the way they are, you're participating in humanity's collective effort to understand reality. That participation matters. It matters because consciousness itself matters. We are the universe's way of knowing itself, and every moment of awareness, every question asked, every sense of wonder felt, all of this is the universe experiencing and exploring its own nature. The future of cosmology is bright. The tools are getting better. The data is accumulating. The theories are being refined. And slowly, patiently, with care and rigor, we're peeling back the layers of mystery that surround the cosmos, revealing truths that our ancestors could barely have imagined. The cosmic axis is just one piece of this grand puzzle. But it's a fascinating piece, a thread that, when pulled, might unravel into something profound, or might simply come loose, revealing that it was never connected to anything substantial in the first place. Time will tell. And we have time. The universe is 13.8 billion years old and will continue for trillions more. Our species has only been asking scientific questions for a few centuries, and we're already learning things that seem impossible. Imagine what we'll know in another century or another millennium if we survive that long and keep asking questions. Let yourself feel hopeful about that future. Even if you won't be here to see all the answers, even if the great mysteries of the cosmos are resolved long after your lifetime, you can take comfort in knowing that the search continues, that others will pick up where we left off, that the journey goes on, generation after generation, each one adding its small contribution to the vast project of understanding. You're part of that project, right now. By thinking about these questions, by listening to this gentle exploration of cosmic mysteries, by allowing yourself to wonder and to be uncertain and to feel connected to something larger than yourself, that's enough. That's beautiful. That's your part in the grand story of consciousness reaching out to comprehend the cosmos. Rest now in that knowledge. Let it settle over you like a soft blanket. You've traveled far tonight, through ancient light and spinning galaxies, through cosmic webs and theoretical frameworks, through uncertainty and wonder and the patient accumulation of knowledge. And tomorrow, the journey continues. Not for you necessarily. You can rest, you can let these ideas fade into dreams if you like. But for someone, somewhere, the journey continues. Telescopes will keep observing. Computers will keep analyzing data. Scientists will keep thinking, questioning, testing, refining. And maybe eventually we'll know. We'll understand why the universe looks the way it does, whether it has hidden axes or perfect symmetry, whether its structure tells a story about its beginning or is just random noise with no deeper meaning. But even if we never know for certain, the search itself is worthwhile, because it makes us more than we were. It stretches our minds. It humbles us with the vastness of what we don't know. It fills us with wonder at what we do know. And it reminds us, always, that we're part of something incomprehensibly large and beautiful, something worth studying, something worth celebrating, something worth drifting off to sleep thinking about, with a quiet smile and a sense of peace. The universe is waiting, patiently, eternally, ready to reveal its secrets to anyone curious enough to ask, careful enough to listen, and humble enough to admit when they don't know. And that includes you. So, does the universe have a hidden axis? Is everything spinning around one point? It's the question that brought us here, whispered softly at the beginning like a child asking if the stars are organized in secret patterns we can't see. And after wandering through the cosmic microwave background, through aligned galaxies and quasar polarizations, through theoretical frameworks and future telescopes, we find ourselves gently circling back to where we began, still wondering. We've learned that the universe might have subtle anisotropies. We've explored how patterns in the oldest light, the CMB, show alignments that shouldn't exist in a perfectly symmetric cosmos. We've discovered that distant galaxies might spin in coordinated ways, that the cosmic web might have preferred orientations, that spacetime itself might carry memories of its violent birth in directions woven through its geometry. We've considered explanations ranging from inflation to topology, from cosmic rotation to observational artifacts, from the multiverse to pure statistical chance. We've seen how scientists approach these mysteries with a mix of curiosity and caution, eager to discover truth but unwilling to rush to conclusions without solid evidence. Maybe the cosmic axis is real. Maybe it's telling us something profound about the universe's initial conditions, about broken symmetries in the early cosmos, about structure in spacetime we never expected to find. Maybe it's a gateway to new physics, new understanding, new ways of seeing reality. Or maybe it's an illusion. Maybe it's a collection of statistical coincidences and subtle systematic errors, patterns that look meaningful but ultimately signify nothing. Maybe the universe is perfectly isotropic after all, and we're just seeing ghosts in the data. Maybe we'll never know for certain. Maybe this is one of those questions that hovers forever at the edge of our ability to answer, tantalizing, but elusive. Maybe that's the whole point. The universe doesn't owe us answers. It simply is, and we're left to wonder, to question, to probe gently at its mysteries with our instruments and our mathematics and our insatiable curiosity. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned a few things about cosmic axes and ancient light and the beautiful uncertainty at the heart of cosmology. Not the worst way to spend a sleepless night. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you surrounded by city lights that hide the stars, or can you see the night sky clearly from where you are? Are you perhaps someone who studies astronomy yourself, or just someone who finds the cosmos strangely comforting? If you found this gentle journey into the hidden axis of the universe relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of science and beyond. Each one of these videos is a labor of love, a quiet space carved out in the noise of the world for wonder and learning and peaceful contemplation. Thank you for joining me on this journey through cosmic patterns and universal mysteries. Sleep well, dream deep, and may your thoughts drift gently through filaments and voids, through ancient light and spinning galaxies, through all the vast spaces where science and wonder meet. Remember, somewhere in the universe, maybe along a hidden axis, maybe in random directions, countless stars are shining, countless galaxies are spinning, and you're connected to all of it, part of the same grand pattern, the same cosmic dance. Close your eyes. Let your breathing slow. Let the universe hold you, rotate around you, whisper its secrets through the darkness. You don't need to understand it all. You just need to be part of it, which you already are, which you always have been, which you always will be. Good night.